hello, and welcome to Sleep with Science, where your mind can rest and your curiosity can wander. Here, science doesn't shout, it flows softly, like moonlight, across still water. Every night, we drift through quiet questions and cosmic stories, letting the universe speak in a slower language. Let's begin. You have arrived, not at a typical destination, but a liminal space, a place apart. Here, at the bottom of the world, the rules are different, the landscape unforgiving, the air impossibly crisp. This is Antarctica, a world where the vastness swallows you whole, where the silence speaks louder than any storm. Take a breath, let the cold seep into your very core. Feel the weight of the ages pressing down upon you, because what you are about to witness is a story written not in ink, but in ice, a story etched by the slow, relentless hand of time. Look around you, really look. This isn't just a picture, postcard of snow and ice. This is an experience, a visceral encounter with the raw, untamed power of nature. It's a landscape that defies superlatives, a place where the word immense feels utterly inadequate. From horizon to horizon, a sea of white stretches before you, broken only by the occasional jagged peak of a distant mountain, like the dorsal fins of some slumbering leviathan rising from the depths. The sheer scale of it can be overwhelming. It's easy to feel insignificant here, a tiny speck lost in a world of ice and snow. And that, in a way, is the point. Antarctica has a way of stripping away the distractions, the anxieties, the petty concerns of everyday life. It forces you to confront your own mortality, your own place in the grand scheme of things. It's a humbling experience, but also a liberating one. Close your eyes for a moment. Block out the image of the screen and just listen. What do you hear? Nothing, perhaps, but listen more closely. There's a silence here, unlike any other you've ever experienced. It's not just the absence of sound. It's a living, breathing entity. It's a silence that hums, that vibrates, that seems to penetrate your very soul. It's a silence so profound that it can almost be deafening. A silence that amplifies the sound of your own heartbeat, the sound of your own breath. It's a silence that invites introspection, that compels you to listen to the whispers of your own inner voice. Imagine a world without the constant barrage of noise that assaults our senses every day. No traffic, no sirens, no chatter, no music, just the pure, unadulterated silence of nature. It's a rare and precious commodity, a gift that Antarctica offers freely to those who are willing to receive it. Open your eyes again. Notice the quality of the light. Here, at the bottom of the world, the sun behaves in strange and wonderful ways. During the Antarctic summer, it never truly sets, circling endlessly above the horizon, casting long, ethereal shadows that dance across the snow. It's a surreal and mesmerizing sight, a reminder that the laws of nature are different here, that the rules are bent and broken in ways that defy our expectations. And during the Antarctic winter, the sun vanishes entirely, plunging the continent into months of perpetual darkness. But even in the darkness, there is light. The stars shine brighter here than anywhere else on Earth, their light undimmed by pollution or atmospheric haze. The moon casts an ethereal glow upon the snow, transforming the landscape into a silvery dreamscape. And the aurora australis, the southern lights, dance across the sky in a shimmering display of color. A celestial ballet that is both breathtaking and awe-inspiring. Feel the cold. It's a cold that bites, that stings, that penetrates through layers of clothing and chills you to the bone. But it's also a clean cold, a pure cold, a cold that carries with it the scent of ice and snow. A scent that is both invigorating and strangely comforting. This isn't the damp, bone-chilling cold of a city winter. This is a dry, crisp cold that feels almost antiseptic. It's a cold that reminds you of the power of nature, the forces that have shaped this landscape for millions of years. It's a cold that demands respect, a cold that reminds you of your own vulnerability. Take a moment to appreciate the simplicity of the landscape. There are no trees here, no forests, no sprawling grasslands, just ice, snow, and rock. It's a minimalist landscape, a canvas painted with the most fundamental elements. But within that simplicity lies a profound beauty, a stark elegance that is both captivating and inspiring. Notice the subtle variations in color, the blinding white of the snow, the deep shadows cast by the low-angled sun. The colors seem to shift with the angle of the sun, with the passing of clouds, with the changing of the light. This is not a landscape of vibrant hues and bustling activity. It's a landscape of subtle nuances, of muted tones, of quiet contemplation. It's a place where you can truly connect with yourself, with the raw power of nature, with the fundamental forces that shape our planet. Antarctica is a place that will stay with you long after you have left. It's a place that will challenge your perceptions, that will test your limits, that will inspire awe and wonder. It's a place that will remind you of the beauty and fragility of our planet and the importance of protecting it for future generations. So, welcome to Antarctica. Your journey begins now. You are standing on the threshold of a world unlike any other. Prepared to be amazed, prepared to be humbled, prepared to be transformed. The secrets of the ice are waiting to be revealed. All you have to do is listen. But even within the seemingly static domain of ice, a subtle ballet unfolds. The illusion of stillness is powerful, convincing even, but it's an illusion nonetheless. Close your eyes, breathe. What sounds break the silence? Or what sounds are masked by the silence? The reality beneath that perception is anything but still. Imagine standing on the surface, but with senses heightened beyond human capabilities. You would perceive a world teeming with subtle movement, a constant exchange of energy and matter. It's not about cataclysmic events, but the persistent, almost imperceptible shifts that shape the landscape over vast stretches of time. It is a constant state of flux and evolution hidden within the grand scale. Think first of the snow itself. We often see it as a uniform blanket, a homogeneous layer of white. But zoom in, focus on a single snowflake. Each one is a miniature masterpiece, a unique crystalline structure formed by the intricate dance of water molecules in the upper atmosphere. Each tiny variation in temperature, humidity, and air pressure during its formation leaves its mark on the crystal's shape, creating an infinite array of unique forms. And these snowflakes aren't static. They are constantly being sculpted by the wind, rearranged into drifts and dunes, their delicate structures slowly eroded by the sun. The wind, an invisible hand, carves intricate patterns on the surface, transforming the landscape into a constantly evolving work of art. These subtle shifts, these miniature avalanches of snow, are a constant reminder that even in the most seemingly stable environments, change is always underway. Consider the ice itself. Beneath the surface layer of snow lies the ancient ice, compressed by centuries of accumulated snowfall. This ice isn't a monolithic block. It's a complex mosaic of crystals, air bubbles, and impurities, a record of past climates frozen in time. It is a slow but steady march of time, each layer a story, each bubble a captured breath of ancient air. Sunlight penetrates the surface, filtering through the layers of ice and snow. The light scatters and refracts, creating a subtle interplay of colors, shades of blue and green that shimmer and dance beneath the surface. It's a hidden luminescence, a secret light show playing out within the frozen depths. Light pierces through, bringing its life-giving energy to the depths of the ice, and subtly melting the surface with each passing day. And listen closely. The silence isn't absolute. There are subtle sounds, whispers on the wind, the creaking of the ice as it expands and contracts with the changing temperatures, the distant groan of a glacier shifting its immense weight, the faint hiss of blowing snow, a sound like the breath of the continent itself. And even deeper, there is the rush of air within the caves and tunnels within the ice, as it flows from one area to another. These sounds are often so subtle that they're easily missed, lost in the vastness of the landscape, but they're there. A constant reminder that even in the seemingly lifeless realm of ice and snow, there is movement, there is change, there is life. These microsonics build to a macro symphony within the ice. Even the seemingly solid rock beneath the ice is not immune to these subtle movements. The immense weight of the ice sheet exerts tremendous pressure on the bedrock below, causing it to slowly deform and subside. This deformation, in turn, affects the flow of ice above, creating a feedback loop that further shapes the landscape. The mountain bends and gives an infinitesimal movement, but a movement nonetheless. Consider the albedo effect, the ability of the white surface to reflect sunlight back into space. This reflection plays a crucial role in regulating Earth's climate, acting as a giant mirror, reflecting heat and keeping the planet cool. Even this reflection creates a micro-melting effect, a constant battle between the radiation of the sun and the solidity of the ice. And what about the organisms that manage to eke out an existence on this frozen surface? Microscopic algae, thriving in the meltwater pools that form during the brief summer months, hardy lichens, clinging to exposed rocks, slowly weathering the stone with their tenacious grip, snow petrels, soaring overhead, searching for a meal. In the icy waters, these are micro-movements of life and death playing out on a daily basis. These organisms are a testament to the resilience of life, to its ability to adapt and thrive in even the most extreme environments. They are a reminder that even in the seemingly barren landscape of Antarctica, life persists, finding a way to carve out a niche in the frozen wilderness. Each tiny movement, each flutter of a wing, each cell dividing, contributes to the grand and subtle dance of life on this frozen continent. So, the next time you see an image of Antarctica, don't just see a frozen wasteland. Look closer, listen more intently, see the intricate patterns in the snow, hear the whispers of the wind, and imagine the subtle play of light beneath the surface. Recognize that the illusion of stillness is just that, an illusion. It is a masterful painting of death over a bustling city of life. Beneath the mask of ice and snow lies a world of hidden motion, of subtle beauty, of enduring life. It's a world waiting to be discovered, a world that challenges our perceptions and invites us to look beyond the surface. And as we begin to peel back the layers of this frozen mystery, we start to see that Antarctica is not just a place of ice and snow. It's a place of profound wonder and enduring mystery. The closer you look, the more you will see is moving, changing, or fighting. It is a world of quiet chaos and hidden movement. This is the truth revealed, but the surface, that vast expanse of white, is a masterful illusion. It suggests a world frozen in time, locked in an eternal embrace of ice. A world of death, perhaps. A world where nothing moves, nothing changes. It lulls you into a false sense of permanence. But look closer, listen more carefully, and most importantly, look deeper. Because beneath that icy mask, a hidden world awaits. A world of flowing water, of slow, deliberate motion, of ancient secrets preserved for millennia. Imagine peeling back the layers of ice, like turning the pages of an ancient book. Each layer tells a story, a chronicle of the Earth's past. But the deepest pages, the ones that have remained untouched for millions of years, are written in water. Liquid water, flowing beneath the crushing weight of the ice. This is the paradox of Antarctica, a continent defined by ice, yet sustained by water. It's a world of contrasts, of contradictions, where the seemingly impossible becomes reality. A place where the very definition of frozen is challenged. We've been conditioned to see ice as static, as unyielding, as the very embodiment of stillness. But consider this, ice is merely water in a different state, and like water, it is dynamic, ever-changing, constantly responding to the forces that act upon it. Even the solid ice of Antarctica flows, albeit at a glacial pace, a slow, relentless river carving its way towards the sea. But the most astonishing aspect of this hidden world isn't the movement of the ice itself, but the existence of liquid water beneath it. Rivers and lakes, vast subterranean reservoirs, teeming with secrets of a bygone era. Now, you might be asking yourself, how is this possible? How can liquid water exist beneath miles of solid ice, in a place where the temperature rarely rises above freezing? The answer, as is so often the case with Antarctica, lies in a complex interplay of geological forces and scientific principles. The first key is the Earth's internal heat. Deep beneath the surface, the planet's core radiates heat outwards, a constant, simmering energy that melts the ice from below. It's a subtle warming, barely perceptible, but over millions of years, it has been enough to create a network of subglacial waterways. Think of it as a giant slow-motion melting pot, where the Earth's internal furnace gently coaxes the ice into a liquid state. It's a geological ballet, a delicate dance between heat and ice, creating a unique and improbable environment. But the Earth's heat is only part of the equation. The other critical factor is pressure. The immense weight of the ice sheet pressing down on the bedrock below creates unimaginable pressure. This pressure lowers the melting point of ice, allowing it to exist in a liquid state even at temperatures below 0 degrees Celsius. It's the same principle that allows ice skaters to glide across the ice. The pressure from their blades melts a thin layer of water, reducing friction and enabling them to move effortlessly. In Antarctica, the scale is vastly different, but the principle remains the same. The crushing weight of the ice sheet forces the ice at its base to melt, creating a lubricating layer that allows the ice to flow, and as the ice melts, it forms rivers, slow, meandering rivers that carve pathways through the bedrock, threading their way through ancient landscapes. These are not the raging torrents you might find in other parts of the world. These are slow, deliberate streams, warmed by the Earth's heat and lubricated by the pressure above. These rivers converge, forming lakes, subglacial lakes, vast reservoirs of ancient water, sealed off from the outside world for millions of years. These lakes are like time capsules, preserving secrets of past climates, of ancient ecosystems, of life forms that have long vanished from the surface. Imagine a world untouched by sunlight, isolated from the atmosphere, a place where time has stood still for millennia. That is the reality of Antarctica's subglacial lakes. They are relics of a different era, offering a unique glimpse into the Earth's past. And these subglacial rivers and lakes aren't isolated phenomena. They're interconnected, forming a complex network of waterways that span the entire continent. This network acts as a hidden circulatory system, transporting water, sediment, and nutrients across vast distances. Even in this seemingly barren environment, life finds a way. Scientists are discovering microbial life in these subglacial lakes and rivers, organisms that have adapted to the extreme conditions of darkness, cold, and pressure. These microbes are a testament to the resilience of life, to its ability to thrive even in the most inhospitable environments. And just how do scientists know about all of this? They use a variety of sophisticated tools, including radar and seismic surveys, to map the hidden landscapes beneath the ice. Radar waves can penetrate the ice, bouncing off the bedrock and revealing the shape of the land below. Seismic surveys use sound waves to create images of the subsurface, revealing the presence of water and other geological features. These technologies are constantly evolving, allowing scientists to create increasingly detailed maps of Antarctica's subglacial world. It's a process of discovery, of exploration, of gradually unveiling the secrets that lie hidden beneath the ice. Now, let's descend from the microscopic artistry of snowflakes and consider the grander scale, the continental ice sheet itself. Let's delve into what truly animates this frozen giant, glacial ice dynamics. We've touched on the illusion of stillness, but let's now confront the reality of relentless motion. Beneath the pristine, seemingly immutable surface, these massive ice sheets are anything but static. They are, in fact, vast, slow-moving rivers of ice, sculpted by gravity and pressure, relentlessly carving their way across the land, shaping the very bedrock beneath. Imagine, if you will, a colossal pancake, but a pancake made of solid ice, miles thick, and spanning entire mountain ranges. Now, envision that pancake slowly, agonizingly slowly, sliding down an inclined griddle, responding to the unwavering pull of gravity. That in essence is what's happening with these glacial ice sheets. The sheer weight of accumulated snow and ice, accumulating over centuries, millennia, even eons, compresses the lower layers, transforming them into a dense, almost plastic-like mass. This extraordinary pressure lowers the melting point of the ice at the base, allowing a thin, lubricating film of water to form, facilitating movement, however imperceptible it may seem. This process, known as basal sliding, is a critical component of glacial flow. It's akin to a gargantuan ice skate gliding across a perpetually wet surface. Only this skate is thousands of feet thick and weighs billions upon billions of tons. The bedrock beneath becomes the rink, and the lubricating meltwater allows for a degree of freedom, a chance for movement against unimaginable friction. But basal sliding isn't the only player in this glacial ballet. The ice itself also deforms under its own colossal weight, a process known as internal deformation. Think of it as squeezing a block of modeling clay. The clay doesn't merely slide, it stretches and bends, adapts and contorts, responding to the applied forces. Similarly, the ice crystals within the glacier slowly realign and slip past one another, allowing the entire mass to flow, however incrementally. The speed of glacial movement varies enormously, depending on a complex interplay of factors: temperature, ice thickness, the presence and distribution of subglacial water, and the underlying geology. Some glaciers, those stoic behemoths clinging to high-altitude valleys, inch along at a truly glacial pace, moving only a few centimeters or even millimeters per year. Others, known as ice streams, those icy expressways that drain vast swaths of the interior, can surge forward at speeds of several meters per day, carving deep channels into the underlying bedrock and transporting colossal quantities of ice towards the restless embrace of the sea. These ice streams are the superhighways of the Antarctic ice sheet, underlain by soft, deformable sediments, layers of ancient mud and silt that further enhance their movement, allowing them to surge forward with surprising speed and force. Consider the Whillans Ice Stream, one of the most intensely studied ice streams in Antarctica. Scientists have discovered that its flow is not a steady, continuous creep. Motion is thought to be intricately linked to the buildup and episodic release of water pressure at the base of the ice stream, a delicate balancing act between friction and lubrication. The sheer force exerted by these relentlessly moving ice sheets is almost incomprehensible to the human mind. They can grind mountains into mere pebbles, carve valleys into the landscape that dwarf our tallest buildings, and transport massive boulders. The evidence of their awesome power is etched into the very fabric of the Antarctic continent, a stark and undeniable testament to the relentless forces that have sculpted this frozen land for countless millennia. Consider Transantarctic Mountains, that formidable range that bisects the continent, a natural barrier to ice flow. Jagged, saw-toothed peaks, and deep, fjord-like inlets that testify to the ice's erosive might. The power of the ice is so immense, so unrelenting, that it has even exposed ancient layers of rock. Movement of glacial ice also plays a crucial role in regulating the global climate system, a connection that underscores the importance of understanding these dynamics. As glaciers flow towards the sea, they eventually calve off into icebergs, those majestic floating islands of ice, contributing significantly to sea level rise, a consequence that directly affects coastal communities around the world. The rate at which glaciers melt and discharge ice into the ocean is therefore a critical factor in predicting future sea level changes and mitigating the impacts of climate change on our planet. Understanding the complex dynamics of glacial ice flow is therefore not just an academic exercise. On this complex process, satellite imagery provides a broad, synoptic overview of ice sheet movement, can penetrate the ice, reveal the topography of the bedrock beneath, and ice cores, those frozen time capsules, provide a detailed record of past climate conditions. Ongoing studies are revealing an increasingly complex and dynamic picture of the Antarctic ice sheet, one that challenges our traditional notions of a static and unchanging landscape. The ice is not inert, it is alive, it is moving, it is shaping the continent and influencing the world around it. As we continue to explore this hidden world, we are gaining a deeper appreciation for the power of ice and the intricate processes that govern its behavior. So, the next time you contemplate an image of Antarctica, don't simply envision a frozen wasteland, a barren expanse of white. Instead, envision it as a land of hidden rivers, ancient lakes, and dynamic ice sheets. Feel the weight, sense the force. Appreciate the slow, deliberate power of the ice as it relentlessly carves its path across the land. And remember, beneath the superficial stillness, there exists a world of constant motion, a world of profound change, a world waiting to be explored and understood. The illusion of tranquility shatters upon closer inspection, revealing a symphony of movement orchestrated by gravity and pressure, a dance of ice that shapes the face of a continent and influences the destiny of our world. Consider the surface again, but this time not as a vast, featureless expanse of white. Imagine shrinking yourself down to the size of a dust mote, drifting on the wind until you land gently on a single snow crystal. What do you see? In the frigid air, no two are ever exactly alike. They are six-sided wonders, born from the fundamental properties of water itself. Think of them as miniature snowflakes. The temperature, the humidity, the wind, all these factors conspire to shape the final form. A slight shift in temperature, a momentary gust of wind, and the crystal's growth pattern changes. Billions upon billions of these intricate structures blanket the Antarctic landscape, creating a surface that is anything but uniform. Look closely, and you'll see a tapestry of textures, a mosaic of miniature sculptures, constantly shifting and evolving. The wind plays a crucial role in this ever-changing artistry. They are echoes of the prevailing winds, frozen in time, telling a story of atmospheric currents and weather patterns. The sun, too, contributes to the constant transformation. As sunlight warms the snow crystals, they begin to sublimate, transitioning directly from solid ice to water vapor, bypassing the liquid phase altogether, softening edges and rounding corners. Imagine the sun's rays filtered through the thin Antarctic air, casting long shadows across the snow-covered landscape. The interplay of light and shadow accentuates the subtle variations in texture, highlighting the intricate details of the snow crystal artistry. Reshaping, and as new snow falls, it blankets the old, burying the previous designs and starting the process anew. Each snowfall is a fresh canvas, an opportunity for the wind and the sun to create new masterpieces. The surface of the Antarctic is not just a static landscape. It's a living, breathing work of art, constantly evolving and transforming. Consider the different types of snow crystals. There are plates, those flat, hexagonal shapes that resemble miniature snowflakes. There are needles, thin, pointed crystals that sparkle in the sunlight. And there are dendrites, those complex, branching crystals that resemble miniature trees. Each type of crystal forms under different atmospheric conditions, and their presence can tell scientists a great deal about the weather patterns and climate of the region by studying the shapes and distribution of snow crystals. They can reconstruct past weather events and gain insights into the long-term climate trends. Think of each crystal as a tiny messenger, carrying information about the atmosphere in which it was born. They are miniature time capsules, frozen records of temperature, humidity, and wind. By deciphering their intricate forms lies not just in its intricate details, but also in its ephemeral nature. These sculptures are not meant to last forever. They are temporary expressions of natural forces destined to melt, sublimate, or be buried beneath new snow. Their beauty is fleeting, transient, all the more precious because of its permanence. So, the next time you see a snowflake, take a moment to appreciate its intricate beauty, its delicate symmetry, its unique and fleeting form. Remember that it is a miniature masterpiece, a testament to the power and artistry of nature. And remember that the same forces that create these tiny wonders are also shaping the vast and majestic landscape of Antarctica, creating a world of hidden beauty and endless fascination. The surface of the ice isn't simply a solid barrier. It's a dynamic interface, a zone of constant interaction between the atmosphere and the frozen depths below. It's a place where the forces of nature are on full display, where the wind, the sun, and the snow conspire to create a landscape of ever-changing beauty. This artistry isn't just something to be admired. It's something to be understood, something to be studied, something to be cherished. It is a reminder that even in the most seemingly barren and inhospitable environments, beauty can be found in the most unexpected places, and it's a testament to the power of nature to create, to innovate, and to surprise us with its endless creativity. But what if I told you that gravity, that invisible force that holds us to the earth, isn't as constant as you might think? What if I revealed that gravity's pull, the very thing that dictates the fall of an apple or the orbit of the moon, varies from place to place, subtly shifting across the face of our planet? We perceive it as a constant, as immutable and unwavering. Stand anywhere, drop an object, and it will fall towards the center of the earth. Simple, definitive, seemingly universal. But reality, as it so often does, hides a more intricate truth. The gravity you experience here in Antarctica, amidst the stark beauty of ice and snow, is not precisely the same as the gravity experienced at the equator, or atop a towering mountain range, or even deep within a subterranean cave. It's a subtle difference, almost imperceptible to our senses, but measurable nonetheless, a whisper in the grand symphony of the cosmos. This variation isn't some esoteric anomaly, some quirk of physics confined to the laboratory. It's a fundamental characteristic of our planet, a consequence of Earth's imperfect shape, its dynamic interior, and even the shifting masses of ice and water that cover its surface. Imagine the Earth not as a perfectly smooth sphere, as we often depict it in textbooks, but as a lumpy, uneven potato, its surface distorted by mountains, valleys, and vast ocean trenches. Now, picture gravity as an invisible net clinging to this uneven surface, its pull varying depending on the density of the material beneath. Where the Earth is denser, where massive deposits of rock or metal lie hidden beneath the surface, gravity's grip is stronger. Conversely, where the Earth is less dense, where lighter materials prevail, gravity's hold weakens. It's a dance of mass and distance, a subtle interplay of forces that shapes the very fabric of our reality. The greater the mass, the stronger the gravitational pull. The further you are from that mass, the weaker the pull becomes. And because the Earth isn't perfectly uniform, because its mass is distributed unevenly, the strength of gravity varies from place to place. Think of it as an invisible landscape, a gravitational terrain that mirrors the topography of the land above. Mountains create peaks in the gravitational field, while valleys create dips. Hidden deposits of dense minerals create localized gravity highs, while underground voids create gravity lows. This invisible landscape is constantly shifting, responding to the dynamic processes that shape our planet. But what causes these variations in density? What lies beneath the surface that could influence the force of gravity in such subtle yet measurable ways? The answer lies in the Earth's complex geological structure, a mosaic of tectonic plates, molten magma, and a diverse array of rocks and minerals, each with its own unique density. Consider the Earth's crust, the outermost layer of our planet, a relatively thin shell composed of a variety of rocks, from the light and porous sedimentary rocks to the dense and crystalline igneous rocks. The thickness of the crust varies significantly, from a mere few kilometers beneath the oceans to over 70 kilometers beneath the towering mountain ranges. This variation in thickness, coupled with the varying densities of the rocks, creates subtle but measurable differences in gravity. Beneath the crust lies the mantle, a vast layer of semi-molten rock that extends nearly halfway to the center of the Earth. The mantle is not uniform in composition, but rather a complex mixture of minerals and elements, some denser than others. These density variations, coupled with the slow, churning motion of the mantle, can also influence the strength of gravity at the surface. And then there's the core, the Earth's innermost layer, a dense sphere of iron and nickel, surrounded by a liquid outer core. The core is the engine of our planet, generating the magnetic field that protects us from harmful solar radiation. The density of the core is immense, far greater than that of the crust or mantle, and its gravitational influence is correspondingly strong. These are the major players in Earth's gravitational drama: the crust, the mantle, and the core. But there are also other, more localized factors that can influence gravity, such as underground reservoirs of water, deposits of ice, and even the presence of large buildings or structures. The vast ice sheets of Antarctica, for example, exert a significant gravitational pull, enough to measurably alter the local gravity field. As these ice sheets melt and shrink due to climate change, their gravitational influence decreases, further highlighting the dynamic nature of our planet. So, as you stand here in Antarctica, surrounded by the seemingly immutable landscape of ice and snow, remember that gravity is not a constant, but a variable, a force that shifts and changes in response to the dynamic processes that shape our planet. It's a subtle force, almost imperceptible to our senses, but measurable nonetheless. A whisper in the grand symphony of the cosmos, a secret code etched into the very fabric of reality. And it's this very variability, this subtle dance of mass and distance, that allows us to probe the hidden depths of our planet, to unlock the secrets that lie buried beneath the surface, and to gain a deeper understanding of the forces that shape our world. So, we've established that gravity holds us to the Earth, keeps the planets in orbit, and generally makes sure things don't fly off into the cosmic void. But what if I told you that gravity isn't a constant force, a uniform blanket enveloping our planet? What if I said that gravity's pull varies, subtly yet significantly, depending on where you are on Earth? It's true everywhere. Fundamental reason: Earth isn't a perfect sphere. We often depict it as a smooth, round ball, but that's a simplification, a convenient fiction. In reality, our planet is more of an oblate, spheroid, a fancy term for a sphere that's squashed at its poles and bulging at the equator. Imagine squeezing a ball from the top and bottom. It would bulge out at the sides, right? That's essentially what's happened to Earth. This bulge, primarily a result of our planet's rotation, significantly impacts gravity's strength. As Earth spun on its axis, the centrifugal force, the same force that pushes you outwards on a merry-go-round, caused the planet to swell around its midsection. This equatorial bulge means that locations at the equator are farther away from the Earth's center than locations at the poles, and that distance is crucial because gravity's strength diminishes with distance. Think of it like a light source. The closer you are to the bulb, the brighter the light. As you move further away, the light becomes fainter. Similarly, the closer you are to the Earth's center of mass, the stronger the gravitational pull. So, at the equator, because you are farther from the Earth's center than you would be at the poles, you experience a slightly weaker gravitational force. It's a subtle difference, but it's measurable. You would weigh slightly less at the equator than you would at the North or South Pole. Now, let's put some numbers to this. The Earth's equatorial radius, that's the distance from the center of the Earth to the equator. The polar radius, the distance from the center of the Earth to either pole, is about 6,357 kilometers, or roughly 3,950 miles. That's a difference of about 21 kilometers, or 13 miles. It may not sound like much on a planetary scale, but it's enough to make a tangible difference in the force of gravity. This difference in radius contributes to about a 0.3% difference in gravity between the equator and the poles. That means if you weigh 100 kilograms, or about 220 pounds, at the North Pole, you would weigh about 99.7 kilograms, or about 219.4 pounds, at the equator. It's not enough to make a noticeable difference on your bathroom scale, but it's a real effect that scientists can measure with sophisticated instruments. But it's not just the distance that matters. The rotation of the Earth also contributes directly to the apparent weight difference. The centrifugal force, that outward push we talked about earlier, acts against gravity. At the equator, this centrifugal force is at its maximum because you're spinning around the Earth's axis at the highest speed. This centrifugal force partially counteracts gravity, making you feel slightly lighter at the poles. However, you're essentially just spinning in place, not moving around the Earth's axis in a significant way. As a result, you experience very little centrifugal force. This means that at the poles, you feel the full effect of gravity, unhindered by the opposing force of rotation. So, the bulge at the equator, coupled with the centrifugal force from Earth's rotation, combine to create a noticeable difference in gravity's pull. You are farther from the Earth's center, and you have the rotation working against gravity at the equator, reducing its force. At the poles, you are closer to the Earth's center, and you have little to no rotational force working against gravity, resulting in a stronger pull. This isn't just an interesting theoretical concept. It has practical implications for things like satellite orbits and even the accuracy of certain types of measurements. Satellites orbiting Earth must account for these gravity variations to maintain their precise trajectories, and scientists who need to make extremely precise measurements, such as those involved in calibrating instruments, need to factor in the local gravity field to ensure accuracy. The Earth's imperfect shape, that subtle bulge at the equator, is a constant reminder that our planet is a dynamic, ever-changing entity. It's not a perfect sphere, fixed and unchanging. It's a living, breathing world, constantly being shaped by the forces of gravity, rotation, and geological processes. And this imperfection, this deviation from the ideal, is what makes Earth so fascinating. It's a source of complexity and diversity, a testament to the power of nature to create unique and unexpected forms. It is this seemingly small detail that has huge implications for, well, pretty much everything. So, remember, the next time you look at a globe, that seemingly smooth, round representation of our planet hides a more complex reality. It's a reality of bulges and dips, of mountains and valleys, of varying densities and hidden structures. It's a reality where gravity's pull is not uniform, but subtly shaped by the Earth's unique form. It's a reminder that even the most fundamental forces of nature are subject to the complexities and imperfections of the world around us. The world and this strange force we call gravity are far more complicated than they seem. But how does the very ground beneath our feet contribute to this gravitational unevenness? It's a question of density, a subtle interplay of mass and volume that shapes the local gravitational field in ways we often overlook. Imagine Earth not as a perfectly uniform sphere, but as a lumpy, heterogeneous ball, with pockets of varying density scattered throughout its crust and mantle. These density variations, caused by differences in the composition of rocks and minerals, exert a subtle but measurable influence on gravity. Think about it. Gravity is a force of attraction between masses. The more mass concentrated in a given volume, the stronger the gravitational pull. So, if you have a region of the Earth's crust packed with dense materials, like iron ore or heavy metal deposits, it will exert a slightly stronger gravitational pull than a region composed of lighter materials, like sedimentary rocks or porous volcanic formations. It's like imagining two mountains, one made of solid granite and the other made of lightweight pumice. Even if they're roughly the same size and shape, the granite mountain, being denser, will have a stronger gravitational pull. This difference in gravitational pull, though subtle, can be detected by sensitive instruments and used to map the hidden variations in density Beneath the surface, the Earth's crust is a complex mosaic of different rock types, each with its own unique density. Igneous rocks, formed from the cooling and solidification of molten magma, tend to be denser than sedimentary rocks, which are formed from the accumulation and cementation of sediments. Metamorphic rocks, formed when existing rocks are transformed by heat and pressure, can have a wide range of densities, depending on their original composition and the degree of metamorphism they have undergone. And within each rock type, there can be further variations in density due to differences in mineral composition. Some minerals, like quartz and feldspar, are relatively light, while others, like magnetite and pyrite, are much denser. The relative abundance of these minerals in a given rock will determine its overall density and consequently its gravitational influence. Consider a large deposit of iron ore buried deep beneath the surface. The high density of the iron ore will create a localized increase in gravity, a gravity anomaly that can be detected by sensitive instruments. These gravity anomalies can be used to locate and map subsurface or deposits, providing valuable information for mineral exploration. Conversely, a large underground cavern or a pocket of low-density volcanic ash will create a localized decrease in gravity, a negative gravity anomaly. These anomalies can be used to identify subsurface voids and geological structures, providing valuable information for geological mapping and hazard assessment. The scale of these density variations can range from a few meters to hundreds of kilometers. Small-scale density variations caused by localized deposits of minerals or variations in rock type will produce small, localized gravity anomalies. Large-scale density variations caused by differences in the thickness and composition of the Earth's crust and mantle will produce broader, more regional gravity anomalies. These gravity anomalies are not just theoretical curiosities. They have real-world applications in a variety of fields. In geophysics, gravity surveys are used to map subsurface geological structures, identify potential oil and gas reservoirs, and monitor changes in groundwater levels. In archaeology, gravity surveys are used to locate buried archaeological sites and artifacts. In engineering, gravity surveys are used to assess the stability of slopes and foundations. The Earth's mantle, the layer of rock that lies beneath the crust, also contributes to gravity variations. The mantle is composed primarily of silicate minerals, but its density varies with depth due to changes in temperature and pressure. These density variations within the mantle can influence the Earth's gravity field on a global scale, deep within the Earth. At the boundary between the mantle and the core lies a region of particularly complex density variations. This region, known as the D layer, is thought to be a graveyard for subducted tectonic plates, the remnants of ancient ocean floor that have sunk deep into the Earth's interior. The presence of these dense, cold slabs of subducted material can create significant gravity anomalies that influence the Earth's geoid, the true shape of the Earth's gravity field. Measuring these subtle variations in gravity requires incredibly sensitive instruments called gravimeters. These devices are designed to detect minute changes in the acceleration due to gravity, allowing scientists to map the density variations beneath the surface with remarkable precision. Airborne and satellite-based gravimetry provides even broader coverage allowing us to map gravity variations over entire continents and oceans. The data collected by these gravimeters is then used to create gravity maps, which are essentially images of the Earth's gravitational field. These maps reveal the hidden density variations beneath the surface, providing valuable insights into the Earth's structure and processes. Think of it like an X-ray of the Earth, revealing the hidden bones and organs beneath the surface. But these gravity maps aren't just static images. They're dynamic representations of a constantly changing planet. As the Earth's tectonic plates move, as mountains rise and erode, as ice sheets grow and melt, the density variations beneath the surface change, and so does the Earth's gravity field. By monitoring these changes in gravity over time, we can gain a deeper understanding of the dynamic processes that are shaping our planet. So, the next time you stand on the Earth's surface, remember that you're not just standing on solid ground. You're standing on a complex and dynamic mosaic of rocks and minerals, each with its own unique density and gravitational influence. You are experiencing the cumulative effect of all these subtle density variations, a symphony of gravitational forces that shape the landscape and influence the very fabric of our planet. It is a constant reminder that even the ground beneath our feet is not as uniform or as unchanging as it might seem. It is a complex tapestry of geological history etched in the language of gravity. Now, let's pull back, zoom out, and consider the bigger picture, the grand topography of our planet. We've explored the minute details, the microscopic artistry of snow crystals, the hidden world beneath the ice. But what about the mountains that pierce the sky, the valleys that carve through the land? Do these colossal features have any impact on gravity? The answer, perhaps unsurprisingly, is a resounding yes. Think of it this way: gravity is a force of attraction, and the more mass you have, the stronger the pull. Mountains, with their immense mass of rock and soil, exert a slightly stronger gravitational pull than the surrounding plains. Valleys, conversely, represent a deficit of mass, a relative absence of material compared to the surrounding highlands. Therefore, they exert a slightly weaker gravitational pull. These variations are subtle, almost imperceptible to our everyday senses. You won't suddenly feel heavier on a mountaintop or lighter in a valley, but they are measurable, detectable, with sensitive instruments called gravimeters, which we'll discuss shortly. These instruments can detect even the tiniest fluctuations in the Earth's gravitational field, revealing the hidden influence of topography. Imagine standing on the slopes of the Himalayas, the towering giants of our planet. Beneath your feet lies an immense mass of rock, extending for miles in every direction. This mass exerts a gravitational pull that is slightly stronger than what you would experience at sea level. It's as if the mountain itself is gently tugging you towards its center, adding a minuscule amount of weight to your frame. Now, picture yourself descending into the Grand Canyon, a vast chasm carved by the Colorado River over millions of years. Here, you are surrounded by empty space, a relative absence of mass compared to the surrounding plateaus. The gravitational pull is slightly weaker in the canyon, as if the Earth is gently releasing its grip, making you feel ever so slightly lighter. These variations aren't just theoretical. They have real-world implications. For example, Surveyors need to take these gravitational variations into account when measuring altitudes. If they were to rely solely on barometric pressure, they would introduce errors due to the varying gravitational pull of mountains and valleys. Gravimeters provide a more accurate way to determine altitude, compensating for the effects of topography on the Earth's gravitational field. Consider also the field of geodesy, the science of measuring and mapping the Earth's shape and gravitational field. Geodesists use gravity measurements to create highly accurate models of the Earth's geoid, which is essentially the true shape of the Earth. Taking into account the variations in gravity caused by topography and density variations, these models are essential for navigation, surveying, and a variety of other applications. The relationship between topography and gravity is not always straightforward. The gravitational pull of a mountain, for example, is not simply proportional to its height. The density of the rock also plays a crucial role. A mountain made of dense basalt will exert a stronger gravitational pull than a mountain made of less dense sandstone, even if they are the same height. Furthermore, the gravitational influence of a mountain extends far beyond its immediate vicinity. The subtle tug of its mass can be felt for hundreds of kilometers, influencing the trajectories of satellites and even affecting the flow of ocean currents. The Earth's gravitational field is a complex and interconnected web, and every topographical feature, no matter how large or small, contributes to its intricate pattern. Think of it like a giant, three-dimensional tapestry, where mountains and valleys are like raised and lowered threads, creating subtle variations in the fabric. Each thread contributes to the overall pattern, and the pattern, when fully understood, reveals the hidden structure of the Earth. The study of these gravitational variations is not just an academic exercise. It has practical applications in a variety of fields. For example, geophysicists use gravity surveys to explore for mineral deposits. Dense ore bodies, such as iron or gold, will exert a stronger gravitational pull than the surrounding rock, creating a detectable anomaly in the Earth's gravitational field. By carefully mapping these anomalies, geophysicists can identify potential areas for mineral exploration. Similarly, gravity surveys can be used to detect underground cavities, such as caves or tunnels. These cavities represent a deficit of mass, and will therefore exert a weaker gravitational pull than the surrounding rock. This technique is particularly useful for detecting hidden sinkholes or underground water reservoirs, and as our planet continues to change due to the forces of climate change, gravity becomes even more important. As ice melts from the polar regions and mountain glaciers shrink, the mass distribution of the Earth changes, leading to subtle but measurable variations in the Earth's gravitational field. By monitoring these changes, scientists can track the rate of ice loss and gain a better understanding of the impacts of climate change on our planet. The Earth is a dynamic planet, constantly evolving and changing, and the Earth's gravitational field is a reflection of this dynamism, a sensitive barometer of the forces that are shaping our world. By studying the subtle variations in gravity caused by topography, we can gain a deeper understanding of the Earth's structure, its history, and its future. So, the next time you stand on a mountaintop, take a moment to appreciate the subtle gravitational pull that you are experiencing. Feel the tug of the Earth beneath your feet, the invisible force that binds us all to this planet. And remember that gravity is not just a constant force. It's a dynamic and ever-changing field, shaped by the mountains, the valleys, and the hidden structures that lie beneath our feet. It's a silent symphony, a constant dance of attraction and repulsion, playing out on a planetary scale. And in the next section, we'll see how scientists are measuring these unseen forces. Now, how do we even begin to detect these minuscule variations in something so seemingly constant as gravity? It's like trying to weigh a feather on a scale designed for elephants. The answer lies in exquisitely sensitive instruments and ingenious techniques, each pushing the boundaries of precision. Let's start with the gravimeter, often described as the workhorse of gravity surveying. In its essence, a gravimeter is a highly refined spring balance. Imagine a weight suspended by a spring, but instead of measuring everyday objects, it's measuring the subtle pull of Earth's gravity on that weight. The beauty of a gravimeter lies in its ability to detect incredibly small changes in the spring's extension. These changes, measured in units called milligauss or microgauss, are directly proportional to the variations in gravity we're trying to detect. To put that in perspective, 1 gal is the acceleration due to gravity at Earth's surface, roughly 9.8 meters per second squared. A milligal is 1,000th of that, and a microgel is 1/1,000,000th. We are talking about detecting incredibly, infinitesimally small changes. There are two main types of gravimeters: absolute and relative. Absolute gravimeters are the gold standard. They determine the absolute value of gravity at a specific location by precisely measuring the acceleration of a free-falling object in a vacuum. It's an incredibly complex and delicate operation, requiring meticulous control of environmental factors and extremely precise timing. Think of it as recreating Galileo's experiments, but with lasers and atomic clocks. These instruments are typically large, expensive, and require specialized expertise to operate. They are like the master standard, used to calibrate and validate other measurements. Relative gravimeters, on the other hand, measure the difference in gravity between two locations. They are more portable and easier to operate than absolute gravimeters, making them ideal for mapping gravity variations over a wider area. You take a reading, move to the next location, take another reading, and the instrument tells you how much stronger or weaker gravity is at that new point relative to the last. This allows for the creation of gravity maps, showing the relative strength of gravity across a region. Imagine meticulously tracing the contours of an invisible landscape, feeling the subtle dips and rises of gravity's pull. But using gravimeters on the ground has its limitations. It's a slow and painstaking process, requiring access to remote locations and careful correction for factors like altitude, terrain, and even the tides. Plus, you can only measure gravity at the surface. What about what lies beneath? That's where the power of space comes in. Satellites, equipped with gravity-measuring instruments, offer a global perspective, allowing us to map Earth's gravity field with unprecedented accuracy and coverage. These satellites don't directly measure gravity in the same way a gravimeter does on the ground. Instead, they rely on clever techniques to infer gravity, variations from subtle changes in their orbits. One of the most successful missions dedicated to mapping Earth's gravity field was the Gravity Recovery and Climate Experiment, or GRACE. Launched in 2002, Grace consisted of two identical satellites flying in tandem about 220 kilometers apart. In a polar orbit around Earth, the key was precisely measuring the distance between these two satellites. As the lead satellite flew over a region with slightly stronger gravity, it would be pulled forward, increasing the distance between the two satellites. Conversely, as it flew over a region with weaker gravity, it would slow down, decreasing the distance. These changes in distance, though incredibly small, on the order of microns, or less than the width of a human hair, were measured with incredible precision using microwave ranging dot by carefully tracking these subtle changes in the satellites' orbits. Scientists could infer the underlying variations in Earth's gravity field. It's like feeling the subtle tug of an invisible hand guiding the satellites through space. The GRACE mission revolutionized our understanding of Earth's gravity, providing invaluable data for studies of ice sheet mass balance, groundwater storage, and sea level rise. Building on the success of GRACE, the GRACE Follow-On mission, or GRACE-FALL, was launched in 2018. GRACE-FALL uses the same basic principle as GRACE, but with an added technological advancement, a laser-ranging interferometer. This instrument uses lasers to measure the distance between the satellites with even greater precision than the microwave ranging system, further improving the accuracy of gravity measurements. In addition to GRACE and GRACE-FO, other satellite missions, such as the European Space Agency's GOCE Gravity Field and Steady-State Ocean Circulation Explorer, have also contributed to our understanding of Earth's gravity field. GOCE used a different approach, employing a gradiometer to directly measure the gravity gradient, or the rate of change of gravity, in 3 dimensions. The data from these satellite missions, a comprehensive picture of Earth's gravity field. This data is then used to create gravity maps, which reveal the subtle variations in gravity across the planet. These maps are not just pretty pictures. They are powerful tools that can be used to study a wide range of geological and hydrological processes. They allow us to see the unseen, to map the invisible, and to unlock the secrets hidden beneath our feet. It is the symphony of space and science at its finest, revealing the subtle, ever-present forces that shape our world. But gravity's uneven embrace doesn't end with the Earth's overall shape. It goes much, much deeper. Literally, the ground beneath your feet, seemingly solid and uniform, is actually a patchwork of varying densities. Different types of rocks, minerals, and geological structures, all packed together like ingredients in some cosmic recipe, exert their own subtle but measurable influence on the local gravitational field. Imagine the Earth not as a perfect sphere, but as a lumpy, slightly misshapen potato. Now, imagine that potato is made up of different layers, like a giant onion, but each layer isn't uniform. It's filled with pockets of denser material, think iron ore deposits, or dense volcanic rock, and pockets of less dense material, perhaps underground caverns filled with air or water. These density variations create what we call asterisk gravity anomalies. A gravity anomaly is simply a deviation from the expected gravitational pull at a given location. It's a tiny difference, often measured in millionths of a meter per second squared, but it's enough to tell us something significant about what lies beneath the surface. Think of it like this. A dense, heavy object exerts a stronger gravitational pull than a lighter object. So, if you were standing directly above a large deposit of iron ore, you would experience a slightly stronger gravitational pull than if you were standing above a large deposit of sandstone, which is less dense. These differences are incredibly subtle, imperceptible to our senses. You won't suddenly feel yourself being pulled more strongly in one direction or another. But, with incredibly sensitive instruments, we can measure these tiny variations with remarkable precision. And this is where things get really interesting. By mapping these gravity anomalies, we can create a picture of the hidden geological structures beneath our feet. It's like having X-ray vision, allowing us to see through the surface and glimpse the secrets hidden deep within the earth. The process is complex, involving meticulous data collection and sophisticated mathematical analysis. But the basic principle is relatively straightforward. We measure the gravitational pull at many different locations, and then compare those measurements to what we would expect based on the Earth's overall shape and density. The differences, the anomalies, tell us about the local variations in density. These gravity measurements are often displayed on maps, using colors to represent the strength of the gravitational pull. Areas with stronger than expected gravity, indicating the presence of denser materials, are typically shown in shades of red or purple. Areas with weaker than expected gravity, indicating the presence of less dense materials, are typically shown in shades of blue or green dot. These maps can reveal a wealth of information about the subsurface. They can show us the location of buried mountain ranges, hidden fault lines, and even the boundaries between different types of rocks. They can help us to understand the complex geological processes that have shaped the Earth over millions of years. Imagine you're an explorer searching for a lost city, buried beneath layers of sediment and vegetation. Traditional methods of exploration might involve digging, probing, and painstakingly excavating the landscape. But with a gravity map, you could potentially identify the location of the city walls and foundations based on their density contrast with the surrounding soil. The city, though invisible to the naked eye, would reveal its presence through its subtle gravitational signature. That's the power of gravity mapping. It allows us to see the invisible, to unveil the hidden structures that lie beneath the surface. It's a technique that's used in a wide range of applications, from mineral exploration to earthquake hazard assessment. For example, gravity surveys are often used to locate underground salt domes, which are important geological structures for the storage of natural gas and the disposal of nuclear waste. Salt is much less dense than the surrounding rock, so salt domes create distinct gravity anomalies that can be easily identified on a gravity map. Similarly, gravity surveys can be used to map the thickness of sedimentary basins, which are geological structures that are often rich in oil and gas deposits. Sedimentary rocks are typically less dense than the underlying basement rocks, so sedimentary basins create gravity anomalies that can be used to estimate their depth and extent. Gravity data is collected in a variety of ways. On land, scientists use sensitive instruments called gravimeters to measure the gravitational pull at different locations. These instruments are incredibly precise, capable of detecting variations in gravity of just a few microgels, a unit of acceleration. Airborne gravity surveys are also conducted using aircraft equipped with gravimeters. These surveys allow scientists to cover large areas quickly and efficiently. But perhaps the most powerful tool for gravity mapping is satellite data. Satellites equipped with gravity sensors can measure the Earth's gravitational field from space, providing a global picture of gravity anomalies. These satellites, like the GRACE Gravity, Recovery, and Climate Experiment and GRACE-FO follow-on missions, have revolutionized our understanding of Earth's gravity field and its variations. The data from these missions is used to create detailed maps of the Earth's gravity field, which are then used to study a wide range of geological and geophysical phenomena, from tracking the movement of magma beneath volcanoes to monitoring the melting of ice sheets in polar regions. Satellite gravity data is providing invaluable insights into the Earth's dynamic processes. So, the next time you look at a map, remember that there's more to it than meets the eye. The Earth is not just a flat, static surface. It's a complex, dynamic planet with a hidden architecture that can be revealed by the power of gravity. The subtle variations in gravity, imperceptible to our senses, hold the key to unlocking the secrets of the Earth's interior. They allow us to map the invisible, to see the unseen, and to gain a deeper understanding of the planet we call home. It's a process of discovery, of unveiling the hidden layers of our world, one gravity anomaly at a time. And it all starts with acknowledging that gravity isn't just a uniform force pulling us downwards, but a subtle and complex field that varies from place to place, revealing the hidden geological story beneath our feet. So we've established that gravity isn't a uniform force, a constant presence acting equally across the Earth. We've seen how the planet's shape, the varying densities of its crust, and the topography of mountains and valleys all contribute to subtle variations in gravitational pull. But what about the unseen? What about the vast quantities of water and ice hidden beneath the surface? How do they impact the local gravity field? The answer, perhaps unsurprisingly, is profoundly. Imagine holding a bowling ball in one hand and a balloon filled with air in the other. Which one feels heavier? Obviously, the bowling ball. This is because the bowling ball is denser. It packs more mass into the same volume. The same principle applies to subterranean water and ice. They may not seem particularly dense compared to rock, but when you consider the sheer scale of these hidden reservoirs, their gravitational influence becomes significant. Let's start with water. Beneath the surface, in aquifers and underground lakes, vast quantities of water accumulate. This water, though less dense than the surrounding rock, still adds mass to the region. The more water present, the stronger the local gravitational pull. It's a subtle effect, a barely perceptible tug, but it's measurable. And, crucially, it's dynamic. Think about it. Aquifers are constantly being recharged by rainfall and snowmelt. They are also being depleted by human activities, like groundwater extraction. These changes in water volume directly affect the local gravity field. When an aquifer fills up, the gravity increases slightly. When it's drained, the gravity decreases. It's a constantly shifting breathing system, and gravity acts as a sensitive barometer, reflecting these fluctuations. Now, let's turn our attention to ice. We've already talked about the massive ice sheets of Antarctica and Greenland. But beneath those ice sheets, and in other regions of the world, lie permafrost, permanently frozen ground, that contains vast quantities of ice. This permafrost acts like a giant frozen sponge, trapping water and organic matter within its icy matrix. Like subterranean water, permafrost influences the local gravity field. The more ice present in the permafrost, the stronger the gravitational pull. But unlike water, which can fluctuate relatively quickly, permafrost changes much more slowly, responding to long-term shifts in climate and temperature. However, that is changing. As the climate warms, permafrost is thawing at an alarming rate. This thawing releases not only water, but also vast quantities of greenhouse gases like methane and carbon dioxide, further accelerating climate change. And, crucially for our discussion, it also alters the local gravity field. When permafrost thaws, the ice melts, reducing the overall density of the ground. This leads to a decrease in the local gravitational pull. It's a subtle change, but one that can be measured by sensitive instruments, providing scientists with valuable data on the extent and rate of permafrost thaw. The story doesn't end there. Consider the phenomenon of subglacial lakes, those hidden bodies of water lurking beneath the Antarctic ice sheet. We've touched on them before, but now let's consider their gravitational impact. These lakes, some of which are hundreds of square kilometers in size, represent significant concentrations of mass beneath the ice. Their presence creates a distinct gravitational anomaly, a localized increase in gravity that can be detected by satellites orbiting high above the Earth. These anomalies are like fingerprints, revealing the location and extent of these hidden lakes. And, just like aquifers, these subglacial lakes are dynamic systems. They fill and drain, sometimes rapidly, influencing the flow of ice above and subtly altering the local gravity field. Measuring these gravitational variations is a challenging task, requiring incredibly precise instruments and sophisticated data analysis techniques. Scientists use gravimeters, highly sensitive devices that measure the acceleration due to gravity. These instruments can detect minute changes in gravity, allowing them to map the distribution of subterranean water and ice. Satellite missions, such as the Gravity Recovery and Climate Experiment, GRACE, and its follow-on mission, GRACEFO, provide a global view of Earth's gravity field. These missions use two satellites flying in tandem, measuring the distance between them with incredible precision. As the lead satellite passes over a region with a stronger gravitational pull, it speeds up slightly, increasing the distance between the two satellites. By measuring these minute changes in distance, scientists can map variations in Earth's gravity field and infer the distribution of mass. Beneath the surface, the data from these missions is invaluable for understanding the dynamics of water and ice on our planet. It allows scientists to monitor changes in groundwater storage, track the melting of glaciers and ice sheets, and assess the impact of climate change on the Earth's water cycle. It also allows us to literally see what is happening underground. These gravity measurements can even provide insights into the structure and composition of the Earth's crust and mantle. By analyzing the gravitational anomalies caused by subterranean water and ice, scientists can better understand the geological processes that shape our planet. It's a fascinating example of how studying something as seemingly simple as gravity can reveal hidden secrets about the Earth's interior. In essence, the gravitational signature of subterranean water and ice provides a window into a hidden world, a world of flowing water, frozen ground, and ancient secrets. By carefully measuring the subtle variations in Earth's gravity field, we can gain a deeper understanding of the dynamics of water and ice and the profound impact they have on our planet. It's a testament to the power of science to reveal the unseen, to connect the dots between seemingly disparate phenomena, and to unlock the mysteries that lie hidden beneath our feet, or, in this case, beneath the ice. Imagine the Earth as a giant, misshapen bowling ball, not perfectly smooth, not uniformly dense. It's got bumps and lumps, heavy spots and light spots, all swirling beneath the surface in a complex geological dance. And that dance affects something we often take for granted: gravity. We think of gravity as a constant, an invisible force pulling us downwards, keeping us anchored to the planet. But the truth is, gravity isn't the same everywhere on Earth. And those subtle variations, those minuscule differences in gravitational pull, can actually help us find buried treasure. Not gold doubloons or pirates' loot, but something arguably even more valuable: mineral deposits. Now, how does this work? It all comes down to density. Different rocks and minerals have different densities. A chunk of iron ore, for example, is much denser than a piece of sandstone. And the denser an object is, the stronger its gravitational pull. So, if there's a large deposit of dense minerals buried underground, it will create a slight increase in the local gravitational field. It's like a tiny, almost imperceptible tug, a subtle enhancement of the Earth's natural pull. This localized increase in gravity is called a gravity anomaly. It's a deviation from the expected gravitational field, a blip on the radar, a signal that something unusual is lurking beneath the surface. And these anomalies are what geologists are looking for when they're searching for mineral deposits. Think of it like this. Imagine you're walking across a perfectly flat field. Suddenly, you feel a slight dip under your feet. That dip is an anomaly, a sign that something is different about that particular spot. It could be a hidden sinkhole, a buried pipe, or, in our case, a deposit of valuable minerals. Of course, the gravity anomalies associated with mineral deposits are incredibly small, far too small to be detected by our own senses. We're talking about variations in gravity that are measured in microgels, which is a unit of acceleration equal to 1/1,000,000th of a centimeter per second squared. To put that into perspective, it's like trying to measure the weight of a single grain of sand on a scale that weighs tons. So how do we measure these tiny variations in gravity? The answer lies in sophisticated instruments called gravimeters. These are incredibly sensitive devices that can detect minuscule changes in the Earth's gravitational field. There are different types of gravimeters, but they all work on the same basic principle. They measure the acceleration of a test mass in a gravitational field. Imagine a weight suspended from a spring. The stronger the gravitational pull, the more the spring will stretch. A gravimeter essentially does the same thing, but with much greater precision. It uses incredibly sensitive sensors to measure the slightest changes in the spring's extension, allowing it to detect even the smallest variations in gravity. These gravimeters can be deployed in a variety of ways. They can be carried on foot, mounted on vehicles, or even installed in aircraft. Each method has its own advantages and disadvantages. depending on the size of the area being surveyed and the desired level of detail. When conducting a gravity survey, geologists systematically measure gravity at a series of points across the area of interest. These measurements are then corrected for various factors, such as latitude, altitude, and the Earth's tides, to isolate the gravity anomalies caused by subsurface density variations. The resulting data is then used to create a gravity map, a visual representation of the gravitational field. This map shows areas of higher gravity, indicating the presence of denser materials, and areas of lower gravity, indicating the presence of less dense materials. By analyzing these gravity maps, geologists can identify potential mineral deposits. A strong gravity anomaly in an area known to contain certain types of minerals is a good indication that there may be a significant deposit buried underground. But gravity surveys are just one tool in the geologist's toolbox. They're often used in conjunction with other geophysical techniques, such as magnetic surveys and seismic surveys, to get a more complete picture of the subsurface. Magnetic surveys measure variations in the Earth's magnetic field, which can be caused by certain types of magnetic minerals. Seismic surveys use sound waves to create images of the subsurface, revealing the structure and composition of the rocks below. By combining data from these different surveys, geologists can create detailed three-dimensional models of the subsurface, allowing them to pinpoint the location, size, and shape of potential mineral deposits. This is crucial because, let's be honest, mining is an expensive business. Drilling exploratory boreholes to confirm the presence of a deposit is costly, time-consuming, and damaging to the environment. Gravity surveys, when combined with other geophysical data, reduce the risk of drilling dry holes, therefore saving time, money, and mitigating the environmental impact. The beauty of using gravity to find mineral deposits is that it's a non-invasive technique. It doesn't require any digging or drilling, and it doesn't disturb the environment. It's a way of seeing beneath the surface without actually having to dig. It's a method of remote sensing, probing the depths of our planet with the invisible hand of gravity. And it's not just about finding new deposits. Gravity surveys can also be used to monitor existing mines, to track changes in the subsurface, and to ensure that mining operations are being conducted safely and responsibly. Think of it as an early warning system, detecting subtle shifts in the ground that could indicate potential problems. So, the next time you think about gravity, don't just think of it as a force that keeps you from floating away. Think of it as a powerful tool, a hidden key that can unlock the secrets of the Earth, revealing the treasures that lie buried beneath our feet. It is a delicate dance, a whisper from the Earth, a message written in the language of mass and acceleration. And for those who know how to listen, it can lead to the discovery of riches beyond imagination beneath our feet. Unseen and unheard in our daily lives lies a world in constant motion. It's a world where immense forces clash, where continents drift, and where the very shape of our planet is perpetually being redefined. This is the realm of tectonic plates, the giant puzzle pieces that make up Earth's lithosphere, and their dance is inextricably linked to the subtle variations in gravity we've been exploring. Imagine the Earth's surface, not as a solid, unyielding shell, but as a cracked eggshell fragmented into these massive plates. These plates aren't stationary. They're constantly moving, albeit at a snail's pace, driven by the immense heat and pressure deep within the Earth's mantle. Some plates collide, crumpling and folding to create mountain ranges. Others slide past each other, generating earthquakes and volcanic activity. Still others pull apart, creating vast rift valleys and new oceanic crust. Each of these interactions has a profound effect on the distribution of mass within the Earth. And as we've learned, mass is the key to gravity. When plates collide and mountains rise, they add mass to a specific location, ever so slightly increasing the gravitational pull in that area. Conversely, when plates separate and rift valleys form, they remove mass, reducing the gravitational force. These changes are subtle, almost imperceptible, but they are real, and they are measurable. Consider the Himalayas, the highest mountain range on Earth. These majestic peaks are the result of the ongoing collision between the Indian and Eurasian plates, a collision that began millions of years ago and continues to this day. The immense mass of the Himalayas has a noticeable effect on gravity, creating a regional gravitational anomaly. A sensitive gravimeter placed on the Tibetan Plateau would register a slightly higher gravitational pull than one placed at sea level. But it's not just the mountains themselves that contribute to this anomaly. The collision between the plates also compresses and thickens the Earth's crust, adding even more mass to the region. This process, known as crustal thickening, is a fundamental part of mountain building, and it plays a significant role in shaping the Earth's gravity field. Now, let's travel to the mid-ocean ridges, the underwater mountain ranges that snake their way across the ocean floor. These ridges are where new oceanic crust is created as tectonic plates pull apart. Magma from the Earth's mantle rises to the surface, cools, and solidifies, forming new crust that gradually spreads outwards. The formation of new oceanic crust also affects gravity. As the magma cools and solidifies, it becomes denser, adding mass to the mid-ocean ridge. However, this increase in mass is often offset by the thinning of the lithosphere beneath the ridge, which reduces the overall gravitational pull. The net effect is a complex interplay of gravitational forces that vary depending on the specific characteristics of the ridge. Perhaps the most dramatic manifestation of tectonic plate movement is subduction, the process by which one plate slides beneath another. This typically occurs when an oceanic plate collides with a continental plate, with the denser oceanic plate sinking into the mantle. Subduction zones are sites of intense geological activity, characterized by earthquakes, volcanoes, and the formation of deep ocean trenches. They also have a significant impact on gravity. As the oceanic plate descends into the mantle, it drags with it vast amounts of water and sediment, which are then recycled back into the Earth's interior. This process alters the density of the mantle, affecting the gravitational pull in the region. The subducting plate itself also adds mass to the mantle, but this is often offset by the removal of material through volcanic eruptions. The net effect is a complex pattern of gravitational anomalies that can be used to map the structure and dynamics of subduction zones. It's important to remember that tectonic plate movement is a very slow process, measured in centimeters per year. The gravitational changes associated with this movement are therefore also very slow, unfolding over millions of years. These are not the kind of changes that we can observe in our lifetimes, but they are nonetheless real and significant. Scientists use a variety of techniques to study the gravitational effects of tectonic plate movement. Satellite gravity missions, such as GRACE and GRACEFO, provide a global overview of the Earth's gravity field, allowing them to track long-term changes in mass distribution. Ground-based gravimeters provide more detailed measurements of gravity variations in specific locations. By combining these data with other geological and geophysical information, scientists can build a more complete picture of the Earth's interior and the forces that shape our planet. They can use gravity data to track the movement of tectonic plates, to map the distribution of mass within the Earth, and to understand the processes that drive earthquakes, volcanoes, and other geological phenomena. So the next time you feel the ground beneath your feet, remember that it's not as solid and stable as it seems. Below the surface, tectonic plates are constantly moving, colliding, and interacting, reshaping the Earth and subtly altering the force of gravity. It's a slow, powerful, and often unseen dance, but it's a dance that shapes our world in profound ways. This seemingly slow dance has shaped the topography we know and feel every day. It's the reason mountains are formed and why earthquakes rumble beneath our homes. It's a force that reminds us that our planet is not a static object, but a living, breathing entity, constantly evolving and changing, a process that extends far beyond our human comprehension of time. This slow, geological ballet is another piece in the puzzle, another layer to the complex story of how gravity isn't uniform across our world, but varies with the ever-shifting masses beneath our feet. Now, let's turn our gaze skyward, not to the ethereal blues and stark whites above, but even further, to the silent sentinels orbiting our planet, Earth-observing satellites. These sophisticated machines are more than just cameras in the sky. They are intricate sensor platforms, equipped with instruments capable of measuring the subtle variations in Earth's gravity field. And it is through these measurements that we can unlock a powerful tool for understanding ice sheet changes in the polar regions. Think of these satellites as celestial scales, meticulously weighing our planet and detecting even the slightest shifts in mass. The principle is simple, yet profound. The more mass an area possesses, the stronger its gravitational pull. Conversely, a decrease in mass results in a corresponding decrease in gravity. Now, consider the immense ice sheets of Greenland and Antarctica. These frozen reservoirs hold vast quantities of water, enough to raise global sea levels by tens of meters should they melt entirely. Changes in the mass of these ice sheets, whether through accumulation of snowfall or loss due to melting and iceberg calving, directly impact the local gravity field. By precisely measuring these gravitational fluctuations, satellites can provide us with a crucial understanding of how these ice sheets are changing over time. It's like having a cosmic yardstick, allowing us to monitor the health of our planet's frozen regions from space. But how exactly do these satellites measure gravity? They don't simply hover in place. They are constantly moving, orbiting the Earth at thousands of miles per hour. As they pass over areas of varying mass, they experience subtle accelerations and decelerations due to the changing gravitational pull. These accelerations are incredibly small, almost imperceptible to measure. Satellites are equipped with highly sensitive instruments called These devices are designed to detect even the slightest changes in velocity, providing a precise measurement of the gravitational forces acting upon the satellite. One of the most successful satellite missions dedicated to mapping Earth's gravity field was the Gravity Recovery and Climate Experiment, or GRACE. This mission, launched in 2002, consisted of two identical satellites flying in tandem, separated by a distance of about 220 kilometers. As the lead satellite encountered a region with a slightly stronger gravitational pull, it would accelerate slightly, increasing the distance between the two satellites. Conversely, as it passed over a region with weaker gravity, it would decelerate, decreasing the separation. By precisely measuring these minute changes in distance, GRACE was able to create a detailed map of Earth's gravity field, and by comparing these maps over time, scientists could track changes in the distribution of mass, including the mass of ice sheets in the polar regions. GRACE provided groundbreaking insights into the dynamics of ice sheet changes. It revealed that both Greenland and Antarctica were losing ice at an alarming rate, contributing significantly to sea level rise. The data also showed that the rate of ice loss was accelerating, raising concerns about the future stability of these frozen regions. But GRACE was not without its limitations. Its relatively coarse resolution meant that it could only detect changes in mass over large areas. It was difficult to pinpoint the exact locations where ice loss was occurring, and to distinguish between different processes contributing to the overall change. To address these limitations, a follow-on mission, GRACE Follow-on, was launched. In 2018, this mission incorporates several technological improvements, including a laser-ranging interferometer that provides even more precise measurements of the distance between the two satellites. GRACE Follow-on is providing scientists with an even clearer picture of ice sheet changes, allowing them to track the contributions of individual glaciers and ice streams to the overall mass loss. The data are also being used to improve our understanding of the processes driving ice sheet melt, such as ocean warming and changes in atmospheric circulation. The information gathered by these gravity missions is not just of academic interest. It has profound implications for policymakers and coastal communities around the world. By accurately measuring ice sheet changes, we can better predict future sea level rise and develop strategies to mitigate its impacts. Imagine a future where coastal cities are regularly inundated by rising seas, displacing millions of people and causing widespread economic damage. This is not a distant threat. It is a real possibility if we fail to address the issue of climate change and the melting of our planet's ice sheets. Gravity measurements from satellites provide us with a critical early warning system, allowing us to track the health of these frozen regions and take action to protect our coastlines. They are a powerful tool for understanding the complex interplay between climate change, ice sheet dynamics, and sea level rise. And beyond the practical applications, there is also a deeper, more fundamental value in these measurements. They remind us of the interconnectedness of our planet, of the delicate balance between the Earth's systems. They highlight the importance of monitoring these changes and understanding the consequences of our actions. So, the next time you look up at the night sky, remember the silent sentinels orbiting our planet, diligently weighing the Earth and providing us with crucial insights into the health of our frozen regions. They are a testament to human ingenuity and a symbol of our commitment to understanding and protecting our planet. But let's now shift our perspective from the grand scale of ice sheets to the vastness of the oceans, and how even the seemingly uniform surface of the sea is subject to the Earth's subtle gravitational variations. We've seen how gravity isn't a constant force. It fluctuates depending on mass. This principle allows us to understand a critical aspect of sea level rise: the redistribution of ocean mass. Conventional wisdom often frames sea level rise solely in terms of melting glaciers and thermal expansion, warming waters occupying more volume. While these are undoubtedly significant factors, they don't paint the entire picture. The reality is far more nuanced, and gravity measurements are revealing the hidden complexities of how sea level rise is unfolding across the globe. Think about it. If a massive ice sheet in Greenland melts, adding billions of tons of water to the ocean, that water doesn't spread evenly across the globe like a perfectly poured drink. Gravity dictates that the ocean mass will redistribute itself in response to several factors, including the very gravitational pull of the melting ice itself. Imagine a bowling ball placed on a trampoline. It creates a dip, right? Now, imagine pouring water onto that trampoline. The water will naturally pool around the bowling ball, drawn towards its mass. The same principle applies to melting ice sheets. As they lose mass, their gravitational pull weakens, causing the surrounding ocean to subtly redistribute itself. The oceans near the source ice melt experience an initial drop, followed by changes in the overall distribution of water around the globe. This phenomenon, known as sea level fingerprints, means that sea level rise isn't uniform. Some regions will experience significantly higher rates of sea level rise than others, while some areas might even see a temporary decline. These fingerprints are complex patterns influenced by the location of melting ice, the Earth's rotation, and the shape of the ocean basins. And how do we detect these subtle shifts in ocean mass? This is where gravity measurements become invaluable. Satellites like the Gravity Recovery and Climate Experiment, or GRACE, and its successor, GRACE-Follow, have revolutionized our understanding of ocean mass changes. These satellites, essentially, weigh the Earth's gravity field from space, detecting even the slightest variations in mass distribution. Imagine two satellites flying in tandem, separated by a fixed distance. As they fly over a region with slightly higher gravity, the lead satellite will be pulled forward, increasing the distance between them. Conversely, as they fly over a region with slightly lower gravity, the lead satellite will slow down, decreasing the distance. These minuscule changes in distance, measured with incredible precision, allow scientists to map variations in Earth's gravity field. By tracking these gravity variations over time, we can monitor changes in ocean mass with unprecedented accuracy. We can see where the oceans are gaining mass, where they are losing mass, and how these changes are related to melting ice sheets, changes in precipitation patterns, and other factors. Furthermore, this data allows us to differentiate between sea level rise caused by thermal expansion and sea level rise caused by the addition of new mass. Thermal expansion caused by warming waters doesn't change the overall mass of the ocean, but the addition of meltwater from glaciers and ice sheets does. By comparing gravity measurements with sea surface height measurements from other satellites, we can disentangle these two components of sea level rise and gain a more complete understanding of the processes at play. The implications of this gravitational perspective on sea level rise are profound. It allows us to make more accurate predictions about future sea level changes, which is crucial for coastal communities around the world. Understanding the regional variations in sea level rise is essential for planning infrastructure, managing coastal resources, and protecting vulnerable populations. Moreover, gravity measurements provide crucial insights into the health of our planet's ice sheets. By monitoring changes in ice mass over time, we can assess the rate of ice loss and project future contributions to sea level rise. This information is vital for informing climate policy and mitigating the impacts of climate change. However, teasing out the gravitational signal of ocean mass change is not without its challenges. Many other factors influence Earth's gravity field, including changes in groundwater storage, tectonic activity, and even atmospheric pressure. Scientists must carefully account for these factors to isolate the signal of ocean mass change. Despite these challenges, gravity measurements are providing a revolutionary new perspective on sea level rise. They are revealing the hidden complexities of ocean mass redistribution, allowing us to make more accurate predictions about future sea level changes and informing strategies for adapting to a changing climate. The silent pull, the unseen weight, tells a global story. So, as the ice sheets continue to melt, adding mass to our oceans, remember that the impact isn't simply a uniform rise in water levels. It's a complex dance of gravity, a shifting of ocean mass that creates a unique fingerprint of sea level change across the globe. And it's thanks to the precise instruments that measure these gravitational whispers from space that we can begin to understand the true scale of the challenge ahead. It's a future written in gravity, read by satellites, and lived by us all. Now, let's turn our attention to a phenomenon that affects us all, yet often goes unnoticed in this context: earthquakes. Can the subtle shifts in gravity we've been discussing offer a key to predicting, or at least better understanding, these seismic events? The very ground we stand on, seemingly solid and unyielding, is constantly being stressed, strained, and occasionally violently shaken. The question is, can we listen to the Earth's whispers before it roars? For decades, seismologists have relied on monitoring for shocks, smaller tremors that sometimes precede a major earthquake. However, foreshocks are not always present, and even when they are, it's difficult to distinguish them from a cluster of normal, unrelated small earthquakes. This makes prediction based solely on seismic data extremely challenging. Enter gravity. The idea is that before an earthquake, the immense stresses building up within the Earth's crust might cause subtle changes in the density of the rocks. Remember how we discussed density variations affecting gravity? Well, these pre-earthquake stress changes, however minute, could theoretically alter the local gravitational field. Think of it like squeezing a sponge. As you compress it, the density increases, and if you could measure it precisely enough, you'd detect a slight increase in its weight or gravitational pull. Now, measuring these tiny gravitational changes is no easy feat. Earthquakes occur deep beneath the surface, and the gravitational signals they might produce are incredibly weak, easily masked by other, larger gravitational variations caused by things like tides, groundwater movement, and even atmospheric pressure changes. We're talking about needing to detect changes that are orders of magnitude smaller than what we normally experience. Imagine trying to hear a whisper in the middle of a rock concert. That's the kind of challenge we're up against. However, advancements in gravimetry, the science of measuring gravity, are making this increasingly possible. Superconducting gravimeters, for example, are incredibly sensitive instruments that can detect minute changes in gravity over time. These instruments, often housed in specially designed underground vaults to minimize external interference, are becoming increasingly sophisticated. Furthermore, satellite missions like GRACE and GRACEFO, which we mentioned earlier, provide valuable data on large-scale gravity changes. Although their resolution is generally too coarse to detect the localized changes associated with individual earthquakes, the research is ongoing, and the results so far are mixed. Some studies have reported observing gravity changes before certain earthquakes. One of the main challenges is isolating the earthquake-related gravity signal from the background noise. Careful consideration of other potential sources of gravity variation, and a healthy dose of skepticism. One area of promising research involves combining gravity data with other types of geophysical measurements, such as seismic data, GPS data, and even electromagnetic signals. The idea is that by integrating multiple datasets, we can get a more complete picture of the processes occurring within the Earth's crust before an earthquake. This multidisciplinary approach might help us to filter out the noise and identify the true precursory signals. Another exciting avenue of research involves using sophisticated computer models to simulate the stress changes that occur before earthquakes and to predict the resulting gravity variations by comparing these model predictions with actual gravity measurements. It's like having a virtual laboratory where we can experiment with different earthquake scenarios and see how they might affect the gravitational field. It's important to emphasize that we're not talking about predicting earthquakes with pinpoint accuracy, knowing exactly when and where a quake will strike. That remains a distant and perhaps even unattainable goal. However, even if we can't predict earthquakes precisely, a better understanding of the processes that lead to them could still be incredibly valuable. It could help us to identify areas that are at higher risk of earthquakes, to improve building codes, and to develop better early warning systems. Imagine a future where we have a network of highly sensitive gravimeters constantly monitoring the Earth's gravitational field, feeding data into sophisticated computer models, and providing us with an early warning of impending seismic activity. It's a challenging vision, but one that is worth striving for. Even if gravity changes don't prove to be a reliable earthquake predictor, the research itself is providing valuable insights into the complex processes that govern our planet. It's helping us to understand how stress builds up within the Earth's crust, how rocks deform under pressure, and how earthquakes are triggered. This knowledge is not only improving our understanding of earthquakes, but also of other geological phenomena, revealing the hidden forces that shape our world. Each new measurement, each new model, each new insight brings us closer to a deeper understanding of our planet. The research into earthquake-related gravity changes is a testament to human curiosity, to our relentless pursuit of knowledge, and to our unwavering determination to understand the forces that shape our world and impact our lives. It's a challenging journey, but one that is full of promise. And even if the ultimate goal of earthquake prediction remains elusive, the knowledge we gain along the way will be invaluable. Let's turn our gaze now to a different kind of earthly drama, one that unfolds not on the surface, but deep within the fiery heart of volcanoes. While gravity might seem like a passive force, a constant downward tug, within these geological powerhouses, we'll explore how scientists use minute variations in gravity to monitor magma flow and predict potential eruptions. Think of a volcano not as a static cone of rock, but as a dynamic system, a plumbing network of molten rock constantly shifting and churning beneath the surface. Magma, that fiery cocktail of molten rock, dissolved gases, and mineral crystals, is less dense than the surrounding solid rock. This density difference is the key to understanding how gravity measurements can help us monitor volcanic activity. Imagine a balloon filled with air submerged in water. The balloon, being less dense than the water, experiences an upward buoyant force. Similarly, a large body of magma beneath a volcano exerts an upward buoyant force on the surrounding crust. This subtle upward push slightly reduces the overall gravitational pull in that area. It's a tiny change, almost imperceptible, but measurable with incredibly sensitive instruments called gravimeters. Now, picture this: magma moving, shifting, accumulating in different chambers beneath the volcano. As the magma moves, the density distribution changes, and so does the local gravitational field. If magma accumulates in a shallow chamber, for example, the gravitational pull in that area will decrease slightly. Conversely, if magma is withdrawn from a chamber, the gravitational pull will increase. These changes, though minuscule, provide valuable information about the inner workings of the volcano. It's like having a sensitive stethoscope pressed against the earth, listening to the subtle rhythm of magma flow. By carefully monitoring these gravity variations over time, scientists can gain insights into the volume, location, and movement of magma beneath the surface. The instruments used to measure these tiny gravitational changes are called gravimeters. These are not your everyday scales. They're incredibly sophisticated devices capable of detecting variations in gravity, smaller than a billionth of the Earth's overall gravitational pull. There are two main types of gravimeters: absolute gravimeters and relative gravimeters. Absolute gravimeters measure the absolute value of gravity at a specific location. These instruments are typically used to establish a baseline gravity value for a region. They're often bulky and require a stable, vibration-free environment for accurate measurements. Relative gravimeters, on the other hand, measure the difference in gravity between two locations. To track changes in gravity over time at multiple locations around a volcano, they're the workhorses of volcanic gravity monitoring. Imagine setting up a network of these relative gravimeters around a volcano, carefully measuring gravity at regular intervals. As magma moves beneath the surface, the gravimeters will detect subtle changes in gravity, providing a real-time picture of the volcano's internal activity. But it's not just about satellites orbiting the Earth can also contribute to volcanic monitoring. Missions like the Gravity Recovery and Climate Experiment or grace, and its successor grace following. Gravity field. While the resolution of satellite gravity measurements is not as high as ground-based gravimeters, they can provide valuable regional context and detect large-scale magma movements. Think of it as having both a stethoscope for close-up listening and a wide-angle lens for capturing the such as seismology and gas measurements to create a comprehensive picture of volcanic activity. Seismometers detect the tremors and earthquakes caused by magma movement, while gas sensors measure the release of volcanic gases, such as sulfur dioxide and carbon dioxide. By integrating these different datasets, scientists can develop more accurate models of volcanic behavior and improve their ability to forecast eruptions. It's like putting together a complex jigsaw puzzle, with each piece of data providing a crucial clue to the overall picture. Now, let's consider a real-world example. Mount Etna in Sicily is one of the most active volcanoes in the world. Scientists have been using gravity measurements to monitor Etna's activity for decades. These studies have revealed complex patterns of magma movement beneath the volcano, including the accumulation of magma in shallow reservoirs and the migration of magma towards the surface prior to eruptions. By carefully analyzing the gravity data. Another example is the Yellowstone caldera in the United States, a supervolcano with the potential for catastrophic eruptions. Gravity measurements have been used to map the underground magma reservoirs beneath Yellowstone and to track changes in magma volume over time. These studies have shown that the magma system beneath Yellowstone is much larger and more complex than previously thought. While there is no immediate threat of a major eruption, ongoing gravity monitoring is crucial for understanding the volcano's behavior and assessing the long-term hazard. The use of gravity measurements in volcanic monitoring is not without its challenges. The gravitational signal from magma movement can be small and easily masked by other factors, such as changes in groundwater levels or atmospheric pressure. Therefore, careful data processing and modeling are essential to isolate the volcanic signal. Scientists use sophisticated statistical techniques to remove noise and extract the relevant information from the gravity data. Despite these challenges, gravity monitoring has become an indispensable tool for understanding volcanic activity and mitigating the risks associated with eruptions. As technology continues to advance, we can expect even more sophisticated gravity instruments and data analysis techniques, further enhancing our ability to listen to the subtle whispers of volcanoes and unlock their secrets. It is through such careful, painstaking observation that we deepen our understanding of this planet and ultimately our place within it. The very ground we stand on is far from still. It breathes, it shifts, and through the magic of science, we can hear it speak. Now, let's turn our attention to a more unsettling truth: the human impact. We've explored how natural processes create subtle shifts in gravity, but what about the impact of our own actions? Can we, through our insatiable appetite for resources, actually alter the very fabric of the Earth's gravitational field? The answer, perhaps unsurprisingly, is yes. The Earth, for all its apparent solidity, is a delicate balancing act, a complex interplay of forces, pressures, and densities. When we extract resources, whether it's water from deep aquifers or minerals from the Earth's crust, we disrupt this balance. We are, in effect, subtly reshaping the Earth. And these changes leave their mark on the gravitational field. Consider mining. Imagine a vast open-pit mine carved into the side of a mountain. Millions of tons of rock and ore are removed, leaving behind a massive void. That void, once filled with dense material, now contains air, which is significantly less dense. This creates what's known as a negative gravity anomaly, a region where the gravitational pull is slightly weaker than the surrounding areas. The scale of some of these mining operations is staggering. They're not just small-scale digs. They are colossal transformations of the landscape, leaving behind scars that are visible from space. And the amount of material removed is equally immense. Billions of tons of ore, rock, and earth, all extracted to fuel our modern lives. This removal of mass isn't just a local phenomenon. While the change in gravity at any single point might be minuscule, the cumulative effect across numerous mining sites around the world can be significant. We are, quite literally, lightening the Earth's load in certain areas. But it's not just the removal of solid materials that affects gravity. The extraction of groundwater also plays a significant role. Groundwater is a vital resource, especially in arid and semi-arid regions, but our reliance on it is placing a tremendous strain on underground aquifers. We are pumping out water at rates that far exceed the natural recharge, leading to a depletion of these underground reservoirs. Now, think about what that means in terms of gravity. Water, while seemingly weightless, is actually quite dense. When we extract vast quantities of groundwater, we are removing significant amounts of mass from the Earth's subsurface. This, too, creates a negative gravity anomaly. The more water we pump out, the weaker the local gravitational pull becomes. The impact of groundwater extraction is particularly pronounced in areas where aquifers are large and heavily exploited. Consider the Central Valley of California, a major agricultural region that relies heavily on groundwater for irrigation. Decades of intensive pumping have led to a significant decline in groundwater levels, resulting in a measurable decrease in gravity. Scientists are using gravity measurements from satellites, like those collected by the GRACE mission, to monitor these changes in groundwater storage. These measurements provide valuable insights into the rate of depletion and the overall health of our aquifers. It's a critical tool for managing this precious resource and ensuring its sustainability for future generations. But the story doesn't end there. The extraction of oil and natural gas also has a subtle but measurable impact on gravity. These resources, like water, are stored underground in porous rock formations. When we extract them, we are essentially emptying these reservoirs, replacing them with air or other fluids that are less dense. This creates, yet again, a negative gravity anomaly. And it's not just the extraction itself, but also the injection of fluids back into the Earth that can affect gravity. Enhanced oil recovery techniques, for example, involve injecting water or other fluids into oil reservoirs to increase production. This can lead to localized increases in gravity as the density of the subsurface increases. The key takeaway here is that our activities, our quest for resources, are subtly altering the gravitational field of the Earth. These changes are small, often imperceptible without sophisticated instruments, but they are real, and they provide a tangible measure of our impact on the planet. Might ask, does this matter? do these tiny gravitational shifts have any real-world consequences? While the direct effects on our daily lives are negligible, the changes themselves serve as indicators. They're like a planetary pulse, telling us something about the state of the Earth's resources and the overall health of our environment. These gravity changes can also provide valuable information for managing our resources more sustainably. By monitoring gravity variations, we can track changes in groundwater storage, assess the impact of mining operations, and optimize the management of oil and gas reservoirs. It's about using gravity not just as a fundamental force to be understood, but as a tool to help us manage our planet more wisely. Furthermore, consider the interplay between resource extraction and other geological processes. For example, the removal of large quantities of material from a mining site can alter the stresses within the Earth's crust, potentially increasing the risk of landslides or even earthquakes, albeit on a small scale. Similarly, the depletion of groundwater can lead to land subsidence, where the ground surface sinks as the underlying aquifers are drained. This can damage infrastructure, increase the risk of flooding, and exacerbate coastal erosion. In essence, the human impact on gravity is a complex issue with far-reaching implications. It's a reminder that our actions, even those that seem localized and insignificant, can have a ripple effect across the planet. And it underscores the importance of understanding and managing our resources sustainably, not just for our own benefit, but for the long-term health of the Earth. As we continue to explore and exploit the Earth's resources, it is imperative that we do so with a greater awareness of the consequences. We must recognize that we are not just extracting materials. We are also subtly reshaping the planet, altering its gravitational field and influencing its long-term stability. The responsibility lies with us to ensure that our actions do not undermine the very foundation upon which our civilization is built. Now, let's look beyond Antarctica, beyond the Earth itself. Let's consider the gravitational dance between our planet, the Moon, and the Sun. You know the Moon causes tides, right? We've all seen the ocean swell and recede, responding to its celestial tug. But what many don't realize is that this same gravitational influence subtly affects Earth's gravity as a whole. Think of it like this. The Moon's gravity pulls on the side of Earth, closest to it more strongly than it pulls on the center of the Earth, and it pulls on the center of the Earth more strongly than it pulls on the far side. This difference in gravitational force is what creates the tidal bulge. It stretches our planet ever so slightly, deforming its shape and, as a consequence, altering the distribution of mass. This stretching isn't just limited to the oceans. The solid Earth itself also experiences a tidal bulge, though it's much smaller and less noticeable than the ocean tides. But it's there, a subtle deformation that ripples through the rock and soil. This solid Earth tide rises and falls, just like the ocean, though by a much smaller amount, typically only a few decimeters. Now, imagine this bulge moving across the Earth's surface as the Moon orbits our planet. As the bulge moves, it shifts the distribution of mass within the Earth. This shift, in turn, causes slight variations in the gravitational field. It's a subtle effect, but it's measurable, and it demonstrates the dynamic interplay between celestial bodies and the ever-changing force of gravity. And the Sun. it too exerts a tidal force on Earth, though its effect is about half as strong as the Moon's. The Sun's immense mass, despite its greater distance, still exerts a significant gravitational pull. The solar tides combine with the lunar tides to create the familiar pattern of spring tides and neap tides. Spring tides occur when the Sun, Earth, and Moon are aligned, amplifying the tidal forces and causing higher high tides and lower low tides. Neap tides occur when the Sun and Moon are at right angles to each other, partially canceling out their tidal forces and resulting in weaker tides. These tidal forces aren't just limited to the oceans and the solid Earth. They also affect the atmosphere, creating atmospheric tides that influence weather patterns and atmospheric circulation. The atmosphere bulges towards the Moon and the Sun, just like the water, though this is even harder to measure. Think about it. The atmosphere is a fluid, just like the ocean, and it's subject to the same gravitational forces. Although the atmosphere is much less dense than water, the sheer volume of the atmosphere means that the atmospheric tides can have a significant impact on weather and climate. These atmospheric tides can influence the formation of clouds, the strength of winds, and the distribution of energy throughout the atmosphere. They can even affect the propagation of radio waves, impacting communication systems. Now, the combined gravitational effects of the Moon and the Sun might seem small compared to the overall force of gravity, but they're far from insignificant. These tidal forces play a crucial role in shaping our planet and influencing its dynamics. They affect everything from ocean currents and weather patterns to the stability of the Earth's rotation. For example, the tidal forces exerted by the Moon are gradually slowing down the Earth's rotation. This is because the tidal bulge created by the Moon acts like a brake, resisting the Earth's rotation and transferring energy to the Moon, causing it to slowly drift further away from Earth. This process has been ongoing for billions of years, and it will continue to shape the future of our planet. The influence of the Moon and Sun on Earth's gravity extends beyond just tides. They also subtly affect the Earth's orbit around the Sun. The gravitational interactions between these three celestial bodies create a complex dance, with each body influencing the motion of the others. The Earth's orbit around the Sun isn't perfectly elliptical. It's slightly perturbed by the gravitational pull of the Moon. This perturbation causes slight variations in the Earth's distance from the Sun, affecting the amount of solar radiation that reaches our planet. These variations, known as Milankovitch cycles, are believed to play a significant role in long-term climate change. These cycles are subtle, but over thousands of years, they can have a profound impact on Earth's climate. They can trigger ice ages, influence sea levels, and alter the distribution of plant and animal life. The gravitational interactions between the Sun, Earth, and Moon are a prime example of the interconnectedness of the cosmos. These celestial bodies are not isolated entities. They are constantly interacting with each other, influencing each other's motion, and shaping the destiny of our planet. To measure these incredibly subtle changes, scientists rely on incredibly precise instruments and techniques. Satellite missions, such as the Gravity, Recovery, and Climate Experiment, or GRACE, play a crucial role. GRACE consisted of two identical satellites orbiting Earth in tandem, measuring the distance between them with extreme accuracy. by monitoring the tiny changes in the distance between the satellites. Scientists can map variations in Earth's gravity field. These variations provide valuable information about the distribution of mass within the Earth, including the effects of tides, ice sheet changes, and groundwater depletion. These data, meticulously collected and analyzed, reveal the intricate details of the gravitational dance between the Earth, the Moon, and the Sun. They allow us to see beyond the surface of our planet and glimpse the hidden forces that shape our world. So, as you stand on the Earth, remember that you are not just being pulled down by the planet's gravity. You are also being tugged, ever so slightly, by the Moon and the Sun. You are part of a celestial ballet, a grand gravitational dance that has been unfolding for billions of years. And that dance is still influencing the world around you in ways both subtle and profound. Variable gravity. The Earth breathing. It sounds almost fantastical, doesn't it? But it's a very real phenomenon, and understanding it is key to unlocking some of our planet's deepest secrets. We tend to think of gravity as a constant, a steadfast force that keeps us anchored to the Earth. And on a day-to-day basis, that's largely true. But if we zoom out, if we take a longer view, we begin to see that gravity is not static. It fluctuates, it changes, it breathes in response to a myriad of dynamic processes unfolding within and around our planet. Imagine the Earth as a living organism, constantly adjusting and adapting to its environment. Just as our bodies undergo subtle changes in weight as we breathe, as we eat, as we move, the Earth's gravity field is constantly shifting in response to changes in mass distribution. What are some of the factors that contribute to this time variable, gravity? Well, let's start with the most obvious: water. Water is a heavy element, and its movement across the Earth's surface has a significant impact on local gravity fields. Think about the monsoon season in India, for example. The torrential rains that inundate the region each year represent a massive redistribution of water mass. This influx of water increases the local gravitational pull, creating a subtle but measurable gravity high. Conversely, during the dry season, as the water evaporates and flows away, the gravity field weakens, creating a gravity low. These seasonal variations in gravity are not just local phenomena, they have global implications. Scientists use satellite gravity missions, like the Gravity Recovery and Climate Experiment, or GRACE, to monitor these changes in water mass on a global scale. By tracking these variations, they can gain valuable insights into the Earth's hydrological cycle, the distribution of freshwater resources, and the impacts of climate change on water availability. But it's not just surface water that affects gravity. Subsurface water, the water stored in aquifers and underground reservoirs, also plays a significant role. The depletion of groundwater resources due to excessive pumping for agriculture or industry can lead to a decrease in local gravity, signaling a loss of mass from the subsurface. Monitoring these changes in gravity can help us manage our water resources more sustainably, preventing overextraction and ensuring the long-term availability of this precious resource. Ice, of course, is another major player in the gravity game. As we've discussed, the Antarctic ice sheet is a colossal reservoir of frozen water, and its melting or growth has a profound impact on global sea levels and local gravity. The GRACE satellites have provided irrefutable evidence of the accelerating loss of ice from Greenland and Antarctica. And this ice loss is reflected in a corresponding decrease in gravity over these regions. But gravity changes aren't just about water and ice. The solid Earth itself is also dynamic. The movement of tectonic plates, the rise and fall of mountains, the flow of magma beneath volcanoes, all of these processes contribute to changes in the Earth's gravity field over time. Think about the slow, grinding collision of tectonic plates along a fault line. As the plates collide, they deform the Earth's crust, creating mountains and valleys. This deformation changes the distribution of mass in the crust, altering the local gravity field. These changes are subtle, but over millions of years, they can become significant. Volcanic activity also has a measurable impact on gravity. The accumulation of magma beneath a volcano increases the local gravity, signaling an impending eruption. Monitoring these changes in gravity can help scientists forecast volcanic eruptions, giving communities time to prepare and evacuate. After an eruption, as the magma cools and solidifies, the gravity field decreases again. Even earthquakes, those sudden and violent jolts that shake our planet, can cause subtle changes in gravity. The redistribution of mass along a fault line during an earthquake can lead to a measurable change in the local gravity field. Some researchers are even exploring the possibility of using gravity measurements to detect precursory signals before earthquakes, potentially providing early warning of these devastating events. The Earth's mantle, that vast layer of semi-molten rock that lies beneath the crust, is also in constant motion. This convection within the mantle drives the movement of tectonic plates and contributes to long-term changes in the Earth's gravity field. Even the Earth's core, that mysterious realm at the center of our planet, may play a role in gravity variations. The slow, churning motions of the liquid iron within the core generate the Earth's magnetic field. And these motions may also contribute to subtle changes in the Earth's gravity field over very long timescales. These dynamic processes, unfolding within and around our planet, create a complex and ever-changing gravity field. Monitoring these changes requires sophisticated instruments and techniques, including satellite gravity missions and ground-based gravimeters. But the effort is well worth it, because by understanding the breathing of our Earth, we can gain valuable insights into its inner workings, its past history, and its future evolution. We've journeyed across shifting snows, peered beneath frozen surfaces, and witnessed the artistry of ice. Now, it's time to grapple with something a bit more abstract, something that shapes this landscape, and indeed the entire planet, in ways we often overlook. Gravity. We experience gravity as a constant, unwavering force. We're tethered to the Earth, pulled downwards with an almost imperceptible intensity that we take for granted. But what if I told you that gravity isn't quite as uniform as we think, that it varies subtly from place to place, fluctuating according to unseen forces and hidden geometries? It's true. Gravity, that fundamental force that governs the cosmos, isn't the same everywhere on Earth. And to truly understand this, we need to introduce a concept as intriguing as it is essential: the geoid. The geoid. Say it aloud. It sounds almost alien, doesn't it? But it's not some futuristic invention or a celestial body light years away. The geoid is, in essence, the true shape of Earth's gravity. Forget the perfectly round sphere you see in textbooks. Forget the slightly squashed oblate spheroid that accounts for Earth's rotation. The geoid is far more complex, far more nuanced, far more real. Imagine the ocean, not as we typically perceive it, tossed by wind and waves, but perfectly still, perfectly calm, responding only to the pull of gravity. This idealized, undisturbed ocean surface is what the geoid represents. It's a hypothetical surface that extends across the entire planet, both over the land and under the oceans, following the mean sea level adjusted for the effects of gravity. Now, here's the crucial point. This hypothetical ocean surface isn't smooth. It's bumpy, undulating, and uneven, mirroring the variations in Earth's gravitational field. Where gravity is stronger, the geoid bulges outwards, as if the water is being pulled more forcefully towards that location. Where gravity is weaker, the geoid dips inwards, as if the water is being pulled less strongly. Think of it as a gravitational map of the Earth, visualized as a three-dimensional surface. The hills and valleys of the geoid represent the variations in gravity, the subtle differences in the Earth's gravitational pull from one location to another. Why is this important? Because the geoid serves as the fundamental reference surface for all our measurements of elevation. When we say that a mountain is a certain height above sea level, we're actually measuring its height relative to the geoid. Traditional methods of measuring height relied on spirit leveling, where surveyors used a series of carefully placed instruments to determine the difference in elevation between 2 points. But spirit leveling only provides relative heights. To determine the absolute height of a point, we need a reference surface, and that reference surface is the Geoid Global Positioning System, or GPS, uses satellites to pinpoint locations on Earth. GPS provides incredibly accurate three-dimensional coordinates, including latitude, longitude, and altitude. However, the altitudes provided by GPS are not directly related to sea level. They are ellipsoid heights, which are measured relative to a mathematically defined ellipsoid, a perfect, smooth, and idealized version of Earth. To convert these ellipsoid heights into orthometric heights, the heights we typically use in everyday life, the ones measured above sea level, we need to know the difference between the ellipsoid and the geoid. This difference is known as the geoid height. An accurate model of the geoid, we wouldn't be able to use GPS to determine accurate elevations. Our maps would be distorted, our construction projects would be misaligned, and our navigation systems would be unreliable. The geoid is more than just a reference surface. It's a window into the Earth's interior, revealing the hidden structures and processes that shape our planet. Variations in the geoid reflect variations in the density of the rocks and minerals beneath the surface. Areas with denser rocks will have a stronger gravitational pull, causing the geoid to bulge outwards. Areas with less dense rocks will have a weaker gravitational pull, causing the geoid to dip inwards. By studying the shape of the geoid, scientists can learn about the distribution of mass within the Earth, gaining insights into the composition of the mantle, the structure of the crust, and the dynamics of plate tectonics. Imagine trying to understand the human body without being able to see inside. You could observe its external features, but you wouldn't know anything about its internal organs, its skeletal structure, or its circulatory system. The geoid is like an X-ray for the Earth, allowing us to see beneath the surface and reveal the hidden structures that lie within. And it's not just about rocks and minerals. The geoid is also influenced by the distribution of water and ice on the planet. Large ice sheets, like the ones covering Antarctica and Greenland, exert a significant gravitational pull, causing the geoid to bulge in those regions. Changes in ice sheet mass due to melting or accumulation can cause the geoid to change over time. Similarly, the distribution of water in the oceans and on land also affects the geoid. Large bodies of water, such as the Amazon River basin, exert a gravitational pull, while areas with depleted groundwater reserves will have a slightly weaker gravitational pull. By monitoring changes in the geoid, scientists can track changes in the Earth's water cycle, gaining insights into the impacts of climate change on our planet. It's a way of weighing the Earth, tracking the movement of water and ice, and monitoring the health of our planet. So, the geoid isn't just an abstract concept, it's a fundamental tool for understanding our planet. It's the true shape of Earth's gravity, a key to unlocking the secrets of the Earth's interior, and a vital instrument for monitoring the impacts of climate change. It's a silent, invisible force shaping the world around us in ways we often fail to appreciate. And here, in Antarctica, where the ice sheet exerts its immense gravitational pull, the geoid reveals its importance more clearly than perhaps anywhere else on Earth. Understanding it is the first step towards truly understanding the forces that sculpt this frozen world. So, how does all of this constantly shifting, gravitationally nuanced reality, impact our daily lives? You might think these subtle variations are insignificant, mere academic curiosities with no bearing on the real world. But the truth is, living with gravity's variations is something we do every single day, often without even realizing it. These tiny shifts are crucial for navigation, engineering, and a whole host of technologies that underpin modern society. Let's start with navigation. Imagine you're a pilot soaring high above the Earth, relying on sophisticated GPS systems to guide you to your destination. GPS, or Global Positioning System, uses a network of satellites orbiting the Earth to pinpoint your location. These satellites constantly transmit signals containing precise time and location data. Your GPS receiver on the plane picks up these signals, calculates the distance to each satellite, and uses that information to determine your position. But here's the catch. GPS relies on incredibly precise atomic clocks, both on the satellites and on the ground. These clocks are so accurate that they can measure time to within a few billionths of a second. At that level of precision, even the slightest difference in gravity can have a significant impact on the clock's timekeeping. Remember Einstein's theory of general relativity. It tells us that time slows down slightly in stronger gravitational fields. So, if the satellites were orbiting in regions of slightly different gravity, their clocks would run at different rates compared to clocks on Earth. Over time, these tiny discrepancies would accumulate, leading to significant errors in GPS positioning. Imagine relying on a map where distances were constantly shifting and distorting. That's the kind of chaos that would ensue if we didn't account for gravity variations. Therefore, GPS systems must incorporate complex gravitational models to correct for these relativistic effects. They use sophisticated mathematical formulas and data from satellites like GRACE and GOCE, which meticulously map Earth's gravity field to ensure that the time signals are accurate and reliable. Without these corrections, your GPS could be off by several meters, or even tens of meters, leading to navigation errors that could have serious consequences, especially for aircraft, ships, and autonomous vehicles. It's not just GPS, though. Inertial navigation systems, or INS, also heavily rely on understanding gravity. INS are self-contained navigation systems that don't depend on external signals like GPS. They use accelerometers and gyroscopes to measure changes in motion and orientation. By integrating these measurements over time, INS can calculate position and velocity. They're commonly used in aircraft, submarines, and missiles, where GPS signals might be unavailable or unreliable. But here's the problem. Accelerometers measure acceleration, which is the rate of change of velocity. Gravity, of course, is also an acceleration, the constant acceleration pulling us towards the Earth's center. So, an accelerometer can't inherently distinguish between the acceleration due to gravity and the acceleration due to the vehicle's motion. Therefore, INS must have a very accurate model of the local gravity field to subtract the gravitational acceleration from the accelerometer readings. If the gravity model is inaccurate, the INS will misinterpret changes in gravity as changes in motion, leading to errors in navigation. Think of it like trying to weigh something on a scale that isn't properly calibrated. Your measurements will be consistently off. Accurate gravity data is even more crucial for long-range ballistic missiles. These missiles follow a parabolic trajectory, arcing high above the Earth before re-entering the atmosphere and striking their target. Their accuracy depends critically on precisely knowing the gravity field along their flight path. Even small errors in the gravity model can cause the missile to deviate from its intended course, potentially missing its target by a significant distance. Beyond navigation, understanding gravity variations is also essential for many engineering projects. For example, when building bridges, dams, or skyscrapers, engineers need to accurately calculate the stresses and strains on the structure. These calculations depend on knowing the precise weight of the materials used, and weight, of course, is directly related to gravity. Variations in gravity can subtly affect the distribution of stress within a structure, particularly in very large structures. Engineers need to account for these variations to ensure that the structure is stable and can withstand the forces acting upon it. Failure to do so could lead to structural weaknesses or even catastrophic collapse. Consider building a very long suspension bridge. The gravitational pull will be slightly different at each end of the bridge due to variations in Earth's shape and underlying geology. These subtle differences in gravity will affect the tension in the suspension cables and the distribution of stress within the bridge deck. Engineers must carefully model these effects to ensure the bridge is safe and stable, even in seemingly mundane applications. Gravity plays a role. For example, in surveying and mapping, accurate gravity measurements are used to determine the precise elevation of points on the Earth's surface. This is crucial for creating accurate topographic maps and for planning infrastructure projects. like roads and pipelines. Furthermore, consider the oil and gas industry. Geophysicists use gravity surveys to locate underground reservoirs of oil and gas. These reservoirs often have slightly different densities than the surrounding rock, causing subtle variations in the local gravity field. By measuring these variations, geophysicists can identify potential drilling sites. Similarly, mining companies use gravity surveys to locate mineral deposits. Dense ore bodies, like iron or gold, create localized increases in gravity. By mapping these gravity anomalies, mining companies can target their exploration efforts more effectively, saving time and money. So, the next time you use your smartphone's GPS to find your way to a new restaurant, remember that you're relying on sophisticated gravitational models that account for the subtle variations in Earth's gravity field. When you cross a bridge or admire a skyscraper, appreciate the fact that engineers have carefully considered the effects of gravity in their design. And when you fill up your car with gasoline, realize that gravity surveys played a role in locating the oil well that produced that fuel. Gravity's variations, though subtle and often unseen, are woven into the fabric of our modern world. They are a silent force shaping our technologies, guiding our travels, and influencing our lives in countless ways. Understanding this force is not just an academic exercise. It's essential for ensuring the safety, accuracy, and efficiency of many of the systems that we rely on every day. The story of gravity is far from complete. What we've explored so far, these subtle variations in Earth's gravitational field, are just the opening chapters of a much grander narrative. A narrative that delves into the very core of our planet and reaches out into the cosmos. So, what does the future hold for gravity research? What secrets are waiting to be unearthed? And what new technologies will help us unlock them? Imagine a future where we can map the Earth's interior with unprecedented precision, not just the crust and mantle, but all the way down to the inner core. Think of it, a three-dimensional gravity map, revealing the density variations, the swirling currents of molten iron, the very architecture of our planet's heart. This isn't just about satisfying our scientific curiosity. It's about understanding the fundamental processes that drive our planet. The Earth's magnetic field, for instance, is generated by the movement of molten iron in the outer core. By studying the subtle variations in gravity caused by these movements, we can gain insights into the dynamics of the magnetic field and potentially even predict its future behavior. Consider the implications. A weakening or shifting magnetic field could leave us vulnerable to harmful solar radiation, disrupt our navigation systems, and even impact our climate. By understanding the forces that govern the magnetic field, we can better prepare for these potential challenges. But the future of gravity research extends beyond our own planet. Imagine using gravity to explore other worlds, to probe the interiors of distant planets and moons, to search for hidden oceans and subsurface structures. Think of Europa, one of Jupiter's moons, a world covered in a thick layer of ice. Scientists believe that beneath that ice lies a vast ocean of liquid water, potentially harboring life. How can we explore this hidden ocean without drilling through miles of ice? Gravity may hold the answer. By carefully measuring the gravitational field around Europa, we can infer the density and distribution of mass beneath the surface. This could reveal the thickness of the ice shell, the depth of the ocean, and even the presence of underwater volcanoes or hydrothermal vents, the kind of environments where life might thrive. And it's not just about finding life elsewhere in the solar system. It's also about understanding how planets form and evolve. By studying the gravitational fields of different planets and moons, we can gain insights into their internal structure, their composition, and their history. This could help us understand how our own planet came to be, how life arose on Earth, and what the future holds for our solar system. Imagine building a network of gravity sensors orbiting the Sun and constantly monitoring the gravitational fields of all the planets and moons. This would provide us with a wealth of data, allowing us to study the interactions between these celestial bodies and to track changes in their internal structure over time. What tools will we use to achieve these ambitious goals? Advanced gravimeters, far more sensitive and precise than anything we have today. These instruments will be able to detect even the tiniest variations in gravity, revealing subtle clues about the Earth's interior and the hidden structures of other worlds. We'll also need more powerful satellites, equipped with sophisticated gravity sensors and advanced data processing capabilities. These satellites will be able to map the Earth's gravitational field with unprecedented accuracy, providing us with a global view of gravity variations and allowing us to track changes over time. And perhaps most importantly, we'll need new theoretical models, new ways of interpreting gravity data and relating it to the underlying physical processes. This will require a collaboration between physicists, geologists, mathematicians, and computer scientists, all working together to unravel the mysteries of gravity. Imagine a world where we can predict earthquakes with greater accuracy by detecting subtle changes in gravity that precede these events. Think of the lives that could be saved, the damage that could be prevented. Imagine being able to monitor the flow of magma beneath volcanoes, predicting eruptions and evacuating communities before disaster strikes. Imagine using gravity to discover new mineral deposits buried deep underground, providing us with the resources we need to build a sustainable future. Or monitoring the depletion of groundwater aquifers, ensuring that we manage our water resources wisely. The possibilities are endless. The future of gravity research is bright, full of potential, and limited only by our imagination. It's a journey into the unknown, a quest to unravel the secrets of our planet and the universe beyond. As we delve deeper into the mysteries of gravity, we are not just learning about the Earth. We are learning about ourselves. We are gaining a deeper appreciation for the forces that shape our world, the forces that make life possible, the forces that connect us to the cosmos. And, in the end, that is the true power of gravity research. Its ability to connect us to something larger than ourselves, to remind us of our place in the vast and intricate web of the universe. It allows us to feel the pulse of the planet, to sense the subtle rhythms of the cosmos, to understand the fundamental forces that govern all things. The future of gravity research is not just about science. It's about wonder. It's about curiosity. It's about our innate desire to explore, to discover, to understand. It's about pushing the boundaries of human knowledge and venturing into the unknown. So, let us embrace the challenges ahead. Let us explore the mysteries of gravity, and let us unlock the secrets that lie hidden beneath our feet and among the stars. Let the earth continue to whisper its secrets. And so, we arrive at a conclusion, but also, perhaps, at a new beginning. We've journeyed from the stark silence of Antarctica to the intricate dance of gravity across our planet. We've seen how this fundamental force shapes the landscapes, influences the oceans, and even reveals hidden treasures beneath our feet. But now, let's step back and consider the profound implications of it all. Let's reflect on gravity, not just as a physical phenomenon, but as a force of life, a constant companion that has shaped our world and enabled our very existence. Imagine, if you will, a world without gravity, a world where everything floats aimlessly, where the atmosphere dissipates into space, where oceans scatter and evaporate, and where there is no up or down, no anchor, no stability. Such a world would be utterly unrecognizable, utterly inhospitable to life as we know it. It is the force that drew together the swirling dust and gas of the early solar system, coalescing them into a molten sphere that would eventually become Earth. It is the force that stratified the planet, pulling the heavier elements towards the core and leaving the lighter elements to form the crust and atmosphere. It is the force that holds our atmosphere in place, protecting us from the harsh radiation of space and providing us with the air we breathe. Think about the oceans, vast and deep, teeming with life. Gravity is the force that confines them to the Earth's surface, preventing them from boiling away into the vacuum of space. It is the force that creates tides, the rhythmic rise and fall of the sea that shapes coastlines, influences ecosystems, and provides a vital link between the land and the ocean. Consider the mountains, majestic and imposing, reaching for the sky. Gravity is the force that limits their height, preventing them from growing indefinitely and collapsing under their own weight. It is the force that drives erosion, the slow but relentless process of weathering and wearing down the mountains, returning their substance to the plains and valleys below. And think about ourselves, beings of flesh and bone, walking upright on this planet. Gravity is the force that holds us to the ground, allowing us to stand, to move, to interact with the world around us. It is the force that shapes our bodies, influencing our bone density, our muscle mass, and our overall physiology. It is the force that dictates the arc of a thrown ball, the trajectory of a raindrop, the fall of a leaf from a tree. Gravity is so ubiquitous, so fundamental, that we often take it for granted. We rarely stop to consider its profound influence on our lives and on the world around us. But without gravity, there would be no earth, no oceans, no mountains, no life. It is the invisible hand that shapes our reality, the silent partner that allows us to exist. The variations in gravity that we've explored, these subtle fluctuations in the Earth's gravitational field, are not mere curiosities. They are clues, whispers from the deep, telling us about the hidden structure and processes of our planet. They reveal the density variations beneath our feet, the movement of tectonic plates, the melting of ice sheets, the shifting of magma beneath volcanoes. They are a window into the Earth's inner workings, a way of understanding the complex and dynamic forces that shape our world. And by understanding these forces, we can better protect ourselves from natural hazards, manage our resources sustainably, and gain a deeper appreciation for the intricate beauty of our planet. Gravity, it turns out, is not just a force to be reckoned with. It is a tool to be used, a source of knowledge to be tapped. Think back to Antarctica, that vast and seemingly desolate continent. We began our journey there, drawn by the silence and the vastness, by the illusion of stillness. But as we've seen, Antarctica is anything but still. It is a dynamic and ever-changing landscape, shaped by the relentless forces of gravity, ice, and wind. And as we continue to explore Antarctica, as we continue to study the Earth's gravitational field, we will undoubtedly uncover new secrets, new mysteries, new insights into the workings of our planet. The journey of discovery is far from over. So, let us end with a sense of wonder, a sense of gratitude, a sense of responsibility. Let us marvel at the power and beauty of gravity, the force that has shaped our world and enabled our existence. Let us be grateful for the intricate and delicate balance of forces that make life on Earth possible. And let us take responsibility for protecting this planet, for understanding its processes, for ensuring that future generations can continue to marvel at its wonders. Gravity is more than just a force, it is a connection between us and the Earth, between the Earth and the cosmos, between the past, the present, and the future. It is a connection that binds us all together, a reminder that we are all part of something larger than ourselves. So look around you, take stock of the world you inhabit, feel the weight of your feet on the ground, hear the wind in the trees, let the sun warm your skin. All of it, every bit of it, owes its existence to the same force, the same invisible hand, the same fundamental principle. You are connected. We are all connected. And it is in that connection that we find our strength, our purpose, and our future. And that, perhaps, is the most profound reflection of all.